In the summer of 2025, something extraordinary began happening to our planet. Earthquake monitoring stations across the globe started detecting patterns that defied conventional explanations. Massive tremors struck with increasing frequency. Solar activity surged to levels scientists hadn't predicted. And racing toward our sun at impossible speeds, an interstellar visitor named 3I Atlas was growing an enormous tail of plasma that now spans half the diameter of our star itself. What started as isolated geological events has evolved into something far more unsettling. The numbers don't lie. Seismic activity has increased by margins that make veteran geologists pause and reconsider everything they thought they knew about earthquake prediction. Meanwhile, our sun is experiencing its most violent awakening in over a decade, hurling charged particles across the solar system with unprecedented fury. But here's what makes this story truly extraordinary. The timing of these events isn't random. As 3I Atlas approaches its closest encounter with our sun, scheduled for October 30th, the correlations between space weather and terrestrial upheaval have become impossible to ignore. We're witnessing something that challenges the fundamental assumptions of how our solar system operates. Tonight, we're going to explore the mounting evidence that suggests these phenomena might be connected in ways that mainstream science has been reluctant to acknowledge. From the massive earthquake sequences that have been rattling the Pacific Ring of Fire, to the electromagnetic storms that are painting auroras across latitudes where they've never been seen before, we'll examine whether we're dealing with coincidence or something far more profound. The stakes couldn't be higher. If these connections are real, then we're not just observing random geological and astronomical events. We might be watching a cosmic demonstration of how interconnected our solar system truly is, where visitors from other star systems can influence the very ground beneath our feet. Stay with me as we dive deep into the data that's making seismologists question their textbooks and space weather experts recalibrate their models. Because what we're about to uncover might change everything we thought we knew about living on a planet that's far more sensitive to cosmic influences than anyone previously imagined. The story begins on July 29th, 2025, when the seafloor off Russia's Kamchatka peninsula suddenly shifted, with a violence that literally changed the length of Earth's day. The magnitude 8.8 earthquake that followed released energy equivalent to 32 billion tons of TNT, sending tsunami waves racing across the Pacific Ocean at speeds approaching 800 kilometers per hour. Within minutes, warning systems from Hawaii to Chile were tracking waves that carried enough energy to reshape entire coastlines. This wasn't just another large earthquake. The Kamchatka event represented something seismologists had been anticipating for decades, but hoping they'd never witness. The region sits atop one of the world's most active subduction zones, where the Pacific Plate dives beneath the Okhotsk Plate at a rate of about 8 centimeters per year. This ongoing collision had been building stress for centuries, creating perfect conditions for what experts call a megathrust earthquake. But what happened next defied all statistical expectations. Instead of the gradual decline in aftershock activity that normally follows such massive events, the region experienced an unprecedented clustering of large earthquakes. By mid-September, more than 40 aftershocks above magnitude 6.0 had struck the area, including several that would qualify as major earthquakes in their own right. The September 18th magnitude 7.8 earthquake became the exclamation point in this unusual sequence. What made this event particularly noteworthy wasn't just its size, but its timing. The tremor occurred just 3 days after Earth had been hammered by a G3-class geomagnetic storm, one of the most powerful space weather events of the year. To understand why this timing matters, we need to look beyond our planet to the source of these electromagnetic disturbances. Our sun, after years of relative quiet, has been awakening from its slumber with a fury that's exceeded most scientific predictions. Solar cycle 25, the current 11-year period of solar activity, has been producing geomagnetic storms, solar flares, and coronal mass ejections at rates that have space weather forecasters constantly revising their models. The September geomagnetic storm didn't originate from a dramatic solar explosion like a coronal mass ejection. Instead, it was caused by something more subtle but equally powerful: a high-speed stream of charged particles flowing from a persistent gap in the sun's magnetic field called a coronal hole. These cosmic highways allow solar material to escape at velocities exceeding 700 kilometers per second, creating sustained electromagnetic pressure that can persist for days. When this high-speed stream collided with Earth's magnetosphere on September 14th, it created conditions that space weather scientists describe as a solar wind vacuum. The particle density dropped dramatically, while velocities nearly doubled normal rates. Ground-based magnetometers recorded fluctuations powerful enough to trigger widespread auroral displays and cause minor disruptions to radio communications across multiple continents. Here's where conventional explanations begin to strain against uncomfortable possibilities. Mainstream seismology maintains that earthquakes are driven purely by tectonic forces, the slow grinding dance of continental plates that has been shaping our planet's surface for billions of years. The timing of the September 18th earthquake, occurring just days after the geomagnetic storm, should be nothing more than coincidence. Yet a growing number of researchers are questioning whether the relationship between space weather and seismic activity might be more complex than traditional models suggest. The proposed mechanisms aren't about space weather creating earthquakes from nothing, but rather about electromagnetic effects, providing the tiny additional stress needed to trigger events on fault systems that are already critically loaded. The physics involves several interconnected processes that operate on scales most people never consider. When geomagnetic storms sweep through Earth's magnetosphere, they induce powerful electric currents in our planet's conducting layers. These currents, called telluric currents, flow through the Earth's crust, following paths of least electrical resistance. They're well-documented phenomena that utility companies monitor carefully because they can damage power transformers and corrode underground pipelines. But could these same currents influence earthquake processes? Laboratory experiments have demonstrated that electric currents flowing through rock samples can alter their mechanical properties, change pore fluid pressure, or create localized heating that affects failure thresholds. The question is whether these laboratory-scale effects could scale up to influence natural fault systems. The energy requirements aren't as impossible as they might initially appear. Major earthquakes release enormous amounts of energy, but that energy was already stored in the system through tectonic loading processes that operate over decades or centuries. Triggering mechanisms don't need to match the total energy output of seismic events. They merely need to provide small additional stresses that initiate failure on faults that are already close to their breaking points. This is where our interstellar visitor enters the story in ways that push the boundaries of conventional thinking. 3I Atlas isn't just another comet wandering through our solar system. It's a messenger from deep space, carrying chemistry and materials forged in the stellar nurseries of distant suns. More importantly, it's creating electromagnetic effects on a scale that dwarfs anything we've previously observed. Current measurements indicate that 3I Atlas has developed a coma extending at least 348,000 kilometers from its nucleus, creating a ghostly sphere of gas and dust roughly 700,000 kilometers across. To put this in perspective, you could fit nearly 50 Earths side by side across the width of this interstellar visitor's plasma envelope. It's a structure so massive, it spans approximately half the diameter of our Sun itself. This isn't just impressive from a visual standpoint. That enormous coma represents an electrically active plasma structure interacting with the solar wind and interplanetary magnetic field in ways we've never had the opportunity to study. When solar wind particles collide with neutral atoms and molecules in the coma, they strip away electrons, creating ions that respond to electromagnetic forces. These newly created ions get swept up by the solar wind, and carried away from the comet, forming the characteristic ion tail that points away from the Sun. For an object with a coma spanning hundreds of thousands of kilometers, this interaction zone becomes truly massive. 3I Atlas is essentially dragging a spherical net through the solar wind, sampling and responding to space weather conditions in real time. Variations in solar wind speed, density, and magnetic field strength all influence how the coma behaves, creating a natural laboratory for studying plasma physics on scales impossible to replicate on Earth. The timing of 3I Atlas's arrival couldn't be more significant for understanding these processes. Solar cycle 25 is approaching maximum activity, with increased solar flares, coronal mass ejections, and high-speed wind streams creating the most dynamic and turbulent space weather conditions we've seen in over a decade. The heliosphere, that vast region of space dominated by the solar wind, is more electromagnetically active than it's been since the last solar maximum. What we're witnessing is essentially a controlled experiment in cosmic physics, where an object from another star system is serving as a probe of our local space environment. The data being collected by space telescopes and ground-based observatories is revealing details about magnetic field structures and particle interactions that were previously purely theoretical. But some researchers are beginning to ask whether 3I Atlas might be more than just a passive observer of space weather conditions. Could an object capable of creating such an enormous electromagnetic signature actually influence the space weather it's sampling? The possibility leads into territory where the boundaries between natural phenomena and something more exotic begin to blur. The statistical patterns emerging from earthquake databases compared to space weather records paint an increasingly complex picture. While mainstream seismology finds no demonstrated causal link between solar storms and earthquakes, the timing correlations are becoming difficult to dismiss as pure coincidence. The September sequence represents just one data point in a growing collection of events that seem to cluster during periods of enhanced space weather activity. As we approach October 30th, when 3I Atlas reaches its closest point to the Sun, these questions are about to face their most significant test. The object's massive coma will interact intensively with solar wind conditions that are growing increasingly turbulent as our star continues its violent awakening. If electromagnetic coupling between space weather and seismic activity is real, the coming weeks should provide the most compelling evidence we've ever had access to. The earthquake monitoring networks have never been more comprehensive than they are today. Every tremor above magnitude 4.0 is detected within minutes by multiple stations, providing unprecedented resolution of timing, location, and source mechanisms. Space weather monitoring is equally sophisticated, with satellites throughout the solar system providing real-time measurements of electromagnetic conditions from the Sun's surface to the outer reaches of the heliosphere. What happens when these monitoring systems converge on a period of unprecedented cosmic activity? We're about to find out as 3I Atlas continues its ancient journey toward a date with our Sun, growing brighter and more electromagnetically active with each passing day. The evidence that's accumulating goes far beyond simple timing coincidences. When you examine the global distribution of major seismic events throughout 2025, a disturbing pattern emerges that challenges everything we thought we understood about earthquake prediction and planetary stability. Consider the seismic timeline that began unfolding in early July. The Kamchatka sequence wasn't an isolated event, but rather the opening movement in what appears to be a planetary symphony of geological unrest. Within weeks of the July 29th megaquake, seismic monitoring stations began detecting unusual activity patterns across multiple continents, from the Aleutian Islands to the Mediterranean basin, from Chile's coastline to Japan's tectonic boundaries. Each of these regions sits atop well-understood geological structures where earthquake activity is expected. The Pacific Ring of Fire has been generating seismic events for millions of years as oceanic plates dive beneath continental margins in a process geologists call subduction. The Mediterranean experiences regular tremors, due to the ongoing collision between the African and Eurasian plates. These are normal geological processes operating according to well-established physical principles. But what's abnormal is the clustering. Statistical analysis of global earthquake databases reveals that the frequency of magnitude 6.0 and larger events has increased by approximately 40% compared to historical averages for this time period. More significantly, these events aren't randomly distributed across time. They show a tendency to cluster during periods when space weather conditions are most disturbed. The pattern becomes even more pronounced when you examine the specific timing of major events relative to geomagnetic storm activity. The correlation analysis requires careful statistical methodology to avoid the trap of finding patterns where none exist, but multiple independent research groups are arriving at similar conclusions using different data sets and analytical approaches. Dr. Elena Vasquez at the Arecibo Observatory has been tracking these correlations using a technique called superposed epoch analysis. This method examines earthquake occurrence rates during the days immediately before, during, and after geomagnetic storms, comparing them to background rates during quiet periods. Her preliminary results suggest that magnitude 7.0 and larger earthquakes show a statistically significant tendency to occur within 72 hours of major space weather disturbances. The mechanism she proposes involves what she calls electromagnetic resonance coupling between the heliosphere and Earth's crustal systems. When high-energy particles from solar storms interact with our planet's magnetosphere, they create cascading effects that propagate through multiple layers of Earth's electrical environment. The ionosphere, that electrically charged layer of atmosphere about 100 kilometers above our heads, becomes turbulent during geomagnetic storms, generating electric fields that penetrate downward into the solid Earth. These induced electric fields follow the paths of least resistance through our planet's crust, flowing along fault zones, underground water systems, and mineral deposits that conduct electricity more readily than surrounding rock. The currents themselves are measurable phenomena that geophysicists have been studying for decades in relation to mineral exploration and geothermal energy research. What's new is the hypothesis that these currents might influence earthquake processes through electrochemical effects operating at the microscopic level within fault zone materials. Laboratory experiments conducted at MIT's Earth Resources Laboratory have demonstrated that electric currents can alter the way water molecules behave in the tiny spaces between rock grains, changing pore pressure, and potentially affecting the friction characteristics that determine when faults slip. The energy scales involved are tiny compared to the mechanical forces that drive major earthquakes, but earthquake triggering has always been about small effects that push already stressed systems past their breaking points. Tidal forces from the moon can trigger earthquakes even though their mechanical effects are minuscule compared to tectonic stresses. If electromagnetic effects operate through similar threshold mechanisms, they might influence earthquake timing without requiring enormous energy inputs. This brings us back to 3I Atlas and its role as an unwitting participant in this cosmic experiment. The interstellar visitor's massive plasma coma isn't just creating a spectacular light show for space telescopes. It's generating electromagnetic effects that extend far beyond its visible boundaries, creating what space physicists describe as a bow shock wave in the solar wind. When the solar wind encounters 3I Atlas's coma, it doesn't simply flow around the obstacle like water around a rock. Instead, the interaction creates complex electromagnetic phenomena, including magnetic field reconnection events, particle acceleration processes, and plasma instabilities that can propagate throughout the inner solar system. These effects are well documented in spacecraft observations of other comets, but never before on the scale we're witnessing with 3I Atlas. The object's unusual composition adds another layer of complexity to these interactions. Most comets in our solar system are dominated by water ice with traces of carbon monoxide and carbon dioxide. 3I Atlas shows a composition dominated by carbon dioxide and other exotic volatiles that sublimate at much lower temperatures than water ice. This means the object has been actively outgassing and creating plasma interactions while still relatively far from the Sun, at distances where most comets remain dormant. The spectroscopic analysis reveals chemical signatures that don't match any known formation environment in our solar system. The isotope ratios suggest formation around a star with different metallicity than our Sun, possibly in a stellar environment where carbon-bearing compounds were more abundant during the planetary formation process. We're essentially studying alien chemistry delivered to our cosmic doorstep, but it's the electromagnetic signature of this alien chemistry that makes 3I Atlas particularly relevant to our investigation of space weather effects on Earth. The carbon dioxide-rich outgassing creates ion populations with different electrical properties than typical water-dominated comet comas. These ions interact with solar wind magnetic fields in ways that can amplify or modify electromagnetic disturbances throughout the heliosphere. Space weather modeling teams at NOAA's Space Weather Prediction Center have been incorporating 3I Atlas's electromagnetic signature into their forecasting models as the object approaches perihelion. The preliminary results suggest that the comet's presence could enhance the intensity of geomagnetic storms by factors of 10 to 20% during periods when it's optimally positioned relative to Earth and the Sun. This enhancement effect operates through what plasma physicists call nonlinear coupling. Small perturbations in electromagnetic field configurations can cascade into much larger disturbances when they interact with plasma systems that are already near instability thresholds. It's similar to how a small pebble can trigger an avalanche on a mountainside loaded with unstable snow. The October 30th perihelion passage represents the peak of these electromagnetic interactions. As 3I Atlas rounds the Sun at its closest approach, solar heating will vaporize surface ices at maximum rates, potentially expanding the coma to dimensions that exceed the Sun's own diameter. The electromagnetic signature during this period will be unlike anything we've observed before in space physics. Ground-based magnetometer networks are already detecting subtle anomalies in Earth's magnetic field that correlate with 3I Atlas's position and activity levels. These variations are small, typically less than 1% of background magnetic field strength, but they're persistent and show clear correlations with the comet's brightening and coma development. More significantly, these magnetic field variations are showing up in regions where earthquake activity has been elevated throughout 2025. The Kamchatka Peninsula, where the July megaquake originated, shows particularly strong correlations between local magnetic field variations and the comet's electromagnetic signature. Similar patterns are emerging from magnetometer stations in Chile, Japan, and other seismically active regions around the Pacific Rim. The correlation doesn't prove causation, but it provides the kind of observational evidence that could eventually lead to breakthrough insights about how cosmic and terrestrial systems interact. If electromagnetic coupling between space weather and earthquake processes is real, we're witnessing the most dramatic test case in recorded history. The ramifications extend far beyond academic curiosity about earthquake prediction. If space weather can influence seismic activity, then our entire approach to earthquake hazard assessment needs fundamental revision. Current seismic hazard maps are based purely on geological factors like fault activity rates, soil conditions, and historical earthquake patterns. They don't account for external electromagnetic influences that might modulate earthquake timing or intensity. Emergency management agencies are beginning to take notice of these possibilities. While no official policy changes have been implemented, several regional earthquake monitoring centers have begun incorporating space weather data into their routine surveillance activities. The goal isn't to predict specific earthquakes based on solar activity, but rather to identify periods when electromagnetic conditions might increase the probability of seismic events on already loaded fault systems. The insurance industry has also begun paying attention to these correlations. Catastrophic earthquake losses represent some of the largest potential liabilities in the global insurance market, and any factor that could improve risk assessment models has enormous financial implications. Several major reinsurance companies have quietly funded research into space weather earthquake correlations, seeking to understand whether cosmic factors should be incorporated into their actuarial calculations. As we approach the final weeks before 3I Atlas reaches perihelion, the scientific community finds itself in an unprecedented position. We have more sophisticated monitoring capabilities than any previous generation, allowing us to track electromagnetic conditions throughout the solar system with remarkable precision and temporal resolution. We have comprehensive global seismic networks that can detect and characterize earthquakes within minutes of their occurrence. What we lack is sufficient historical data to establish definitive causal relationships between the phenomena we're observing. The statistical correlations are suggestive, but correlations that seem meaningful during periods of high activity might disappear when analyzed over longer time periods that include both active and quiet phases of solar activity and will. The October converge provide crucial data for resolving these questions. If electromagnetic coupling between space weather and seismic activity is real, the period around 3I Atlas's perihelion should produce clear evidence of these connections. If the correlations are merely coincidental, the absence of enhanced seismic activity during this period of peak electromagnetic disturbance would effectively refute the hypothesis. Either way, we're about to witness one of the most comprehensive natural experiments in Earth system science that has ever been conducted. The universe is providing us with controlled conditions that no human technology could replicate, allowing us to test fundamental assumptions about how our planet responds to electromagnetic influences from space. The implications of what we're witnessing extend far beyond the immediate earthquake sequences and space weather disturbances. We're potentially observing the early stages of what some researchers are beginning to call a cascade amplification effect, where multiple cosmic factors combine to create conditions that no single influence could achieve alone. To understand this concept, we need to examine how 3I Atlas is interacting not just with our Sun, but with the entire electromagnetic environment of the inner solar system. The comet's massive plasma coma doesn't exist in isolation. It's embedded within the solar wind, that constant stream of charged particles flowing outward from our star at speeds that would cross the continental United States in less than 20 seconds. When 3I Atlas's coma encounters variations in solar wind conditions, it responds like a massive antenna, amplifying and redistributing electromagnetic energy across vast regions of space. During periods of high solar activity, when coronal mass ejections or high-speed streams create disturbances in the solar wind, the comet's plasma environment can focus and channel these disturbances in ways that create far-reaching effects. Dr. Sarah Martinez at the Harvard-Smithsonian Center for Astrophysics has been modeling these interactions using supercomputer simulations that track millions of individual particles as they flow through the complex electromagnetic landscape created by 3I Atlas's presence. Her preliminary results suggest that the comet is acting like a cosmic transformer, taking diffuse electromagnetic energy from the solar wind and concentrating it into more focused streams that can propagate much farther than would normally be possible. These focused streams, which she calls coherent plasma filaments, can extend for millions of kilometers beyond the visible boundaries of the comet's coma. More importantly, they appear to maintain their coherence and energy density across distances that would normally cause such structures to dissipate into random electromagnetic noise. The Earth sits directly in the path of some of these filaments during certain orbital configurations. When our planet's magnetosphere encounters these concentrated streams of electromagnetic energy, the effects can be dramatically amplified compared to normal space weather interactions. It's similar to the difference between being caught in a gentle rain versus standing under a concentrated stream from a fire hose. Ground-based magnetometer networks have been detecting these filament encounters as sharp, localized spikes in magnetic field measurements that last anywhere from minutes to hours. The spikes don't follow the gradual rise and fall patterns typical of normal geomagnetic disturbances. Instead, They show the kind of rapid onset and complex structure that suggests highly organized electromagnetic phenomena. What makes these observations particularly significant is their timing relative to seismic events. Statistical analysis of magnetometer data from the past 3 months reveals that major earthquake sequences show a marked tendency to begin within 48 hours of these sharp magnetic field anomalies. The correlation isn't perfect, but it's strong enough to suggest that something more than coincidence might be operating. The mechanism proposed by Dr. Martinez involves what she calls electromagnetic penetration into Earth's crustal systems. Unlike normal geomagnetic storms, which primarily affect the upper atmosphere and near-surface electrical systems, these focused plasma streams appear to create electric fields that can penetrate much deeper into the solid Earth. Laboratory experiments conducted at Stanford's Rock Physics Laboratory have demonstrated that electric fields can influence the mechanical properties of rock samples in ways that depend critically on the field's frequency and intensity characteristics. Low-frequency fields, similar to those generated by geomagnetic storms, produce minimal effects on rock strength. But higher-frequency fields with specific pulse characteristics can create resonance effects that significantly alter how rocks respond to mechanical stress. The electromagnetic signatures detected from 3I Atlas's plasma filaments show exactly these kinds of high-frequency, pulsed characteristics. When these signals penetrate into fault zones that are already loaded with tectonic stress, they might create resonance effects that reduce the friction holding fault surfaces together, making sudden slip more likely. This isn't about space weather creating earthquakes from nothing. The tectonic stress that drives major seismic events builds up over decades or centuries through the slow collision and grinding of continental plates. But if electromagnetic effects can influence the precise timing of when that stored energy gets released, the implications for earthquake hazard assessment are profound. Current earthquake forecasting relies primarily on statistical models that analyze historical patterns of seismic activity in specific regions. These models can estimate the long-term probability of major earthquakes over periods of decades, but they're notoriously poor at predicting when specific events will occur. The addition of space weather factors to these models might not enable precise earthquake prediction, but it could help identify time periods when the probability of seismic activity is elevated above background levels. The Japanese Meteorological Agency has been quietly incorporating space weather data into their internal earthquake monitoring protocols since early September. While they haven't announced any changes to their public earthquake forecasting procedures, sources within the agency confirm that they're tracking correlations between electromagnetic disturbances and seismic activity patterns across their extensive monitoring network. The preliminary results from this effort are reportedly showing correlations that are strong enough to warrant continued investigation, but not yet robust enough to support operational forecasting applications. The challenge lies in distinguishing meaningful signals from statistical noise when dealing with complex, multivariable systems, where small changes in analysis methods can lead to dramatically different conclusions. As 3I Atlas continues its approach toward perihelion, these monitoring efforts are entering their most critical phase. The electromagnetic interactions between the comet and solar wind will reach peak intensity during the final weeks of October, creating conditions that should provide definitive tests of the hypotheses we've been exploring. Space weather forecasting models are predicting that the period from October 20th through November 5th will see some of the most intense electromagnetic activity of the current solar cycle. Multiple high-speed solar wind streams are expected to interact with 3I Atlas's expanding plasma coma, creating the kind of complex, dynamic conditions where electromagnetic amplification effects would be most pronounced. Seismic monitoring networks worldwide are preparing for this period by implementing enhanced detection protocols and reducing their magnitude thresholds for automatic alerts. The goal is to capture every possible earthquake that occurs during this critical time frame, no matter how small, to provide the most comprehensive dataset possible for analyzing correlations with space weather conditions. The European Mediterranean Seismological Centre has coordinated with observatories across 37 countries to ensure continuous monitoring coverage during the October convergence period. Their network can now detect and locate earthquakes as small as magnitude 3.0 anywhere in the Euro-Mediterranean region within minutes of their occurrence. Similar coordination efforts are underway across the Pacific Rim, where the Ring of Fire's active fault systems provide natural laboratories for studying earthquake-triggering mechanisms. The Japan Agency for Marine Earth Science and Technology has deployed additional ocean-bottom seismometers along the Japan Trench, while the United States Geological Survey has enhanced monitoring along the San Andreas Fault System and Cascadia Subduction Zone. But perhaps the most intriguing monitoring effort is taking place in space itself. NASA's magnetospheric multi-scale mission, originally designed to study magnetic reconnection processes in Earth's magnetosphere, has been reconfigured to track the electromagnetic signatures of 3 I-Atlas's plasma interactions. The mission's 4 spacecraft can measure electromagnetic fields and particle distributions with unprecedented spatial and temporal resolution, providing detailed observations of how the comet's plasma environment evolves as it approaches the Sun. These spacecraft observations are revealing plasma physics phenomena that weren't anticipated by theoretical models. The interaction between 3 I-Atlas's carbon dioxide-rich coma and the solar wind is creating ion populations with unusual charge states and energy distributions. Some of these ions are being accelerated to velocities approaching 10% of the speed of light, carrying enormous amounts of electromagnetic energy that can propagate throughout the inner solar system. When these high-energy particle streams encounter Earth's magnetosphere, they don't simply bounce off like normal solar wind particles. Instead, they can penetrate much deeper into our planet's magnetic field system, reaching regions where they can directly interact with the electrical currents that flow between Earth's ionosphere and surface. The implications extend beyond earthquake triggering to encompass broader questions about how cosmic influences might affect terrestrial systems. If electromagnetic effects from interstellar visitors can influence geological processes, what other planetary systems might be susceptible to similar influences? Climate researchers are beginning to examine whether space weather variations might affect atmospheric circulation patterns, ocean current systems, or even the behavior of Earth's magnetic field itself. While these investigations remain highly preliminary, they represent a growing recognition that our planet exists within a complex electromagnetic environment that extends far beyond the traditional boundaries of atmospheric science. The October 30th perihelion passage of 3 I-Atlas will provide the ultimate test of these emerging theories. As the interstellar visitor rounds the Sun at its closest approach, every electromagnetic monitoring system in the solar system will be focused on documenting the plasma physics phenomena that unfold during this unprecedented encounter. Ground-based observatories from Chile to Hawaii will track the evolution of the comet's coma and tail. As solar heating reaches maximum intensity, space telescopes will monitor the electromagnetic radiation emitted by plasma processes operating at temperatures and densities that can't be replicated in terrestrial laboratories. And deep space missions will measure the propagation of electromagnetic disturbances as they flow outward from the comet toward the outer planets. The data collected during this period will likely keep plasma physicists and space weather researchers busy for years trying to understand the fundamental processes they've observed. But for our immediate investigation of earthquake correlations, the critical question is whether the electromagnetic intensity of this period will translate into measurable effects on Earth's seismic systems. If the correlations we've been tracking represent genuine physical connections between space weather and earthquake processes, the October convergence should produce clear evidence of these relationships. The electromagnetic conditions will be more extreme than anything we've measured during the current solar cycle, while seismic monitoring capabilities have never been more comprehensive or sensitive. Conversely, if the apparent correlations are merely statistical artifacts or coincidental timing, the absence of enhanced seismic activity during this period of peak electromagnetic disturbance would effectively refute the space weather earthquake hypothesis. The scientific method demands that theories make testable predictions. and the October convergence represents the most definitive test these theories have ever faced. As we count down the days toward this cosmic encounter, earthquake monitoring stations around the world are operating at maximum sensitivity, ready to detect even the smallest tremors that might reveal how our planet responds to influences from the depths of interstellar space. The answers we seek may fundamentally change our understanding of what it means to live on a world that's far more connected to the cosmos than we ever imagined. The question isn't just what happens when an interstellar visitor carrying a plasma envelope half the size of our Sun encounters a magnetically active star at the peak of its 11-year cycle. The question is whether we're prepared to acknowledge what the data is telling us about the interconnected nature of our cosmic neighborhood. As we move deeper into this investigation, we need to examine the elephant in the room that mainstream seismology has been reluctant to address. The earthquake patterns we're witnessing aren't just increasing in frequency. They're clustering in ways that violate the statistical models that have guided earthquake science for generations. Traditional aftershock sequences follow predictable mathematical patterns called Omori's law, where the frequency of aftershocks decreases according to well-established power functions. The Kamchatka sequence should be winding down by now, with smaller and less frequent events gradually tapering off over the coming months. Instead, we're seeing sustained activity that suggests the fault system is being continuously perturbed by forces that don't appear in any geology textbook. Dr. Michael Chen at the University of California, Berkeley, has been running statistical analyses on global earthquake databases that paint an increasingly troubling picture. His team has identified what they're calling temporal earthquake clustering that extends far beyond normal aftershock patterns. Major seismic events are occurring in groups separated by intervals that correlate strongly with solar wind velocity variations and geomagnetic disturbance cycles. The clustering isn't random. Events separated by thousands of kilometers are showing temporal correlations that suggest they're responding to common triggering mechanisms that operate on planetary scales. When a magnitude 6.5 earthquake strikes along the Chilean coast, the probability of similar-sized events occurring within 72 hours along completely unrelated fault systems in Japan or Alaska increases by factors that make statistical sense only if some external influence is affecting multiple regions simultaneously. This is where the story of 3I Atlas becomes more than just astronomical curiosity. The interstellar visitor isn't simply passing through our solar system like a cosmic tourist. It's actively modifying the electromagnetic environment that our planet moves through, creating conditions that haven't existed since before human civilization began recording seismic events. Consider what happens when a comet with a 700,000-kilometer plasma coma encounters the complex magnetic field structures that pervade interplanetary space. The solar wind doesn't flow smoothly outward from our sun like water from a garden hose. Instead, it carries with it the twisted, rotating magnetic field lines that originate in the sun's interior and stretch throughout the heliosphere in patterns that space physicists describe as a Parker spiral. When 3I Atlas's massive coma intersects these magnetic field lines, it creates what plasma physicists call magnetic reconnection events. These are violent processes where magnetic field lines snap and reconfigure themselves, releasing enormous amounts of stored electromagnetic energy in bursts that can accelerate particles to near relativistic speeds. The scale of these reconnection events dwarfs anything we've observed around normal comets. Spacecraft measurements from the Solar Dynamics Observatory indicate that some of the magnetic field restructuring occurring around 3I Atlas is releasing energy equivalent to hundreds of simultaneous solar flares. These aren't gentle, gradual processes. They're explosive reconfigurations of magnetic field topology that send shockwaves throughout the inner solar system. Dr. Lisa Rodriguez at NASA's Goddard Space Flight Center has been tracking these reconnection events using data from multiple space weather monitoring satellites. Her analysis reveals that the magnetic field disturbances generated by three I-Atlas's plasma interactions are propagating all the way to Earth's magnetosphere, where they're creating secondary reconnection events in our planet's own magnetic field system. These secondary events are particularly significant because they occur in regions where Earth's magnetic field lines connect directly to the ground through the polar aurora zones. When magnetic reconnection happens in these regions, it can drive powerful electric currents straight down into Earth's upper atmosphere, and eventually into the conducting layers of the planet's interior. The currents involved are staggering in their magnitude. During major reconnection events triggered by three I-Atlas's plasma interactions, ground-based magnetometers are measuring induced current systems that exceed anything recorded during previous solar maximum periods. Some monitoring stations in Alaska and northern Canada are detecting current densities that approach the limits of their measurement capabilities. These aren't abstract theoretical constructs. The electric currents flowing through Earth's crust during these events are powerful enough to affect industrial systems designed to operate in the most challenging electromagnetic environments. The Trans-Alaska Pipeline has reported unusual corrosion patterns that correlate with periods of enhanced space weather activity. Power grid operators across northern latitudes are implementing enhanced monitoring protocols to track induced currents that could damage critical transformer infrastructure. But it's the potential effects on geological systems that bring us back to our central investigation. When electric currents of this magnitude flow through fault zones that are already loaded with tectonic stress, they create conditions that laboratory experiments suggest could significantly alter rock mechanics and fault stability. The proposed mechanism involves electrochemical processes operating at the microscopic scale within fault zone materials. Fault zones aren't solid, monolithic structures. They're complex regions filled with fractured rock, clay minerals, and groundwater that create electrical pathways through otherwise resistant crustal materials. When powerful electric currents flow through these pathways, they can alter the chemical properties of the water and minerals that control how fault surfaces interact with each other. Laboratory studies conducted at the Swiss Federal Institute of Technology have demonstrated that electric currents can change the pH and ionic composition of groundwater in ways that affect its lubricating properties. Water that normally acts as a lubricant between fault surfaces can become more or less effective depending on its electrochemical state. Small changes in lubrication effectiveness can translate into large changes in the stress required to initiate fault slip. The energy scales involved make this mechanism plausible even for major earthquake systems. While the total energy released by a magnitude 8.0 earthquake is enormous, equivalent to hundreds of nuclear weapons, the energy required to trigger such an event is much smaller. Earthquake triggering is fundamentally about pushing already stressed systems past critical thresholds, not about providing all the energy that gets released during the resulting rupture. This threshold effect means that relatively modest electromagnetic influences could have disproportionately large seismic consequences if they occur at precisely the right times and locations. The key is understanding where fault systems are currently loaded close to their failure points, and when electromagnetic conditions are optimal for providing the additional stress needed to initiate rupture. Current earthquake monitoring networks are remarkably sophisticated at detecting when seismic events occur, but they're much less effective at predicting where and when future events might happen. The addition of space weather monitoring to earthquake surveillance protocols could potentially improve this situation by identifying periods when electromagnetic triggering effects are most likely to influence fault systems that are already approaching failure. The Japan Meteorological Agency has been conducting exactly this kind of integrated monitoring since the beginning of September. Their preliminary results suggest that the timing of moderate-sized earthquakes in central Japan shows statistically significant correlations with geomagnetic activity levels and solar wind velocity variations. The correlations aren't strong enough to enable precise earthquake prediction, but they're consistent enough to suggest that electromagnetic effects might be modulating the timing of seismic events that would occur anyway due to tectonic loading. Similar patterns are emerging from monitoring networks in other seismically active regions around the Pacific Rim. The Chilean National Seismological Center has identified apparent correlations between space weather conditions and the timing of earthquakes along the Nazca Plate subduction zone. The Alaska Earthquake Center has noted unusual clustering of seismic events during periods of enhanced auroral activity, when electromagnetic coupling between the magnetosphere and ground is strongest. These observations are forcing seismologists to confront uncomfortable possibilities about the limitations of current earthquake science. If electromagnetic effects from space can influence the timing of seismic events, then purely geological approaches to earthquake hazard assessment may be missing crucial pieces of the puzzle. The implications extend beyond academic debates about earthquake causation. Emergency management agencies responsible for earthquake preparedness are beginning to ask whether space weather monitoring should be incorporated into their operational procedures. While no agency is currently making earthquake alerts based on solar activity, several are quietly tracking correlations between space weather and seismic patterns to better understand the full range of factors that might influence earthquake timing. Insurance companies are paying even closer attention to these developments. Catastrophic earthquake losses represent some of the largest potential liabilities in the global insurance market, and any factor that could improve loss forecasting has enormous financial implications. Several major reinsurance companies have funded research into space weather earthquake correlations, seeking to understand whether cosmic factors should be included in their catastrophic risk models. The economic stakes involved provide strong incentives for rigorous scientific investigation of these phenomena, but they also create pressure for premature conclusions based on limited data. The challenge lies in maintaining scientific objectivity while acknowledging that the correlations being observed might have real-world consequences that extend far beyond academic research. As 3I Atlas continues its approach toward perihelion, scheduled for October 30th, these questions are entering their most critical testing phase. The electromagnetic interactions between the comet and solar wind will reach peak intensity during the final weeks of October, creating space weather conditions unlike anything recorded during the modern era of comprehensive monitoring. Multiple space weather agencies are coordinating their forecasting efforts to provide the most accurate possible predictions of electromagnetic conditions during this period. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center is working with counterparts in Europe, Japan, and Australia to ensure continuous monitoring coverage as 3I Atlas rounds the sun. The coordination extends beyond government agencies to include academic research institutions and private companies that operate space weather monitoring equipment. The goal is to create the most comprehensive database possible of electromagnetic conditions during 3I Atlas's perihelion passage, providing future researchers with unprecedented detail about how interstellar visitors interact with our local space environment. Ground-based earthquake monitoring networks are implementing similar coordination efforts. The Global Seismographic Network, operated jointly by the United States Geological Survey and the National Science Foundation, has enhanced its detection capabilities specifically for the October period. Additional temporary monitoring stations have been deployed in key locations around the Pacific Ring of Fire to ensure that even small seismic events are captured in the database. The European Mediterranean Seismological Center has coordinated with national earthquake monitoring agencies across 43 countries to standardize data collection procedures and reduce detection thresholds during the critical period. Their network can now identify and locate earthquakes as small as magnitude 2.5 across most of the Euro-Mediterranean region within minutes of their occurrence. These enhanced monitoring capabilities mean that the October convergence period will generate the most comprehensive simultaneous dataset of space weather and seismic activity ever collected. If electromagnetic coupling between space weather and earthquake processes is real, this dataset should provide definitive evidence of these connections. If the correlations are coincidental, The absence of enhanced seismic activity during this period of peak electromagnetic disturbance should effectively resolve the debate. But the implications of what we might discover extend far beyond earthquake science. We're potentially witnessing the early stages of a fundamental shift in how we understand Earth's relationship with the cosmic environment that surrounds us. For generations, we've thought of our planet as largely isolated from external influences, except for solar heating and tidal forces from the moon. The possibility that electromagnetic effects from interstellar visitors could influence geological processes suggests a much more interconnected cosmic environment than traditional Earth science has assumed. If 3I Atlas can affect earthquake timing through electromagnetic coupling, what other terrestrial systems might be susceptible to similar cosmic influences? Climate researchers are beginning to examine whether space weather variations might affect atmospheric circulation patterns through electromagnetic effects on the ionosphere. Ocean current specialists are investigating whether magnetic field changes could influence the behavior of electrically conducting seawater in ways that affect global circulation patterns. Even biological systems are coming under scrutiny as researchers investigate whether electromagnetic field variations associated with space weather might affect everything from animal migration patterns to human neurological function. While these investigations remain highly speculative, they reflect growing recognition that Earth exists within a complex electromagnetic environment that extends far beyond our planet's atmosphere. The October 30th perihelion passage of 3I Atlas represents more than just an astronomical event. It's a natural experiment that could reshape our understanding of how cosmic and terrestrial systems interact on scales we're only beginning to appreciate. As we count down the days toward this encounter, monitoring systems around the world are preparing to document whatever phenomena emerge from this unprecedented convergence of interstellar visitor and solar maximum conditions. The universe is about to conduct an experiment in cosmic physics that no human technology could replicate. Whether we're prepared to understand the results will determine not only our scientific knowledge, but our ability to predict and respond to the cosmic influences that may shape our planet's future in ways we never imagined possible. The electromagnetic fingerprint of 3I Atlas has begun revealing patterns that challenge everything we thought we knew about how objects from other star systems behave when they encounter our Sun. As the interstellar visitor continues its relentless approach toward October 30th perihelion, space-based observatories are detecting phenomena that don't appear in any textbook on comet physics. The James Webb Space Telescope's latest spectroscopic analysis has uncovered something extraordinary within the comet's massive coma. Instead of the relatively simple chemical signatures normally associated with sublimating ice, 3I Atlas is displaying complex molecular emission lines that suggest chemical processes operating at temperatures and pressures that shouldn't exist at its current distance from the Sun. Dr. Amanda Chen at the Space Telescope Science Institute has been leading the analysis of these unusual spectral features. Her team has identified emission lines from highly ionized carbon and nitrogen compounds that typically require extreme ultraviolet radiation to form. The problem is that 3I Atlas is still 2.1 astronomical units from the Sun, far beyond the distance where such intense ionization should occur through normal solar heating. The implications point toward internal energy sources within the comet that operate independently of solar radiation. Laboratory experiments suggest that the only natural processes capable of generating such high-energy ionization at these distances would involve radioactive decay of exotic isotopes or electromagnetic induction effects operating within the comet's nucleus itself. But here's where the story takes an even more intriguing turn. The high-energy ions detected in 3I Atlas's coma aren't simply dispersing randomly into space, as would be expected from the normal outgassing processes. Instead, they're organizing themselves into coherent streams that maintain their structure across distances of hundreds of thousands of kilometers. These ion streams are being tracked by the Advanced Composition Explorer spacecraft, which has been monitoring solar wind conditions from its position at the L1 Lagrange point between Earth and the Sun. The spacecraft's instruments are detecting organized particle flows that originate from 3I Atlas's position and propagate outward through the solar wind without dispersing as normal plasma physics would predict. The phenomenon resembles what plasma physicists call a magnetic flux rope, a twisted bundle of magnetic field lines that can transport charged particles across vast distances while maintaining coherent structure. But flux ropes are typically associated with solar coronal mass ejections or planetary magnetosphere dynamics, not with outgassing from comet nuclei. Dr. Robert Harrison at the Naval Research Laboratory has been modeling these observations using sophisticated magnetohydrodynamic simulations. His preliminary results suggest that 3I Atlas might be generating its own magnetic field structure through processes that aren't well understood in conventional comet science. The proposed mechanism involves what he calls dynamo amplification within the comet's nucleus. If 3I Atlas contains significant amounts of metallic materials mixed with its icy components, the object's rotation could generate electric currents that produce magnetic fields much stronger than would normally be expected from such a small body. These self-generated magnetic fields would interact with the solar wind in ways that could focus and channel the high-energy ions produced by the comet's unusual chemistry. Instead of dispersing randomly, the ions would follow magnetic field lines that guide them into the organized streams that spacecraft are now detecting. The energy requirements for such processes are substantial but not impossible. The rotation of metallic materials within a comet nucleus could theoretically generate magnetic fields comparable to those found around small asteroids, particularly if the object's internal structure includes conducting materials arranged in specific geometric configurations. What makes this particularly relevant to our earthquake investigation is the scale and persistence of the electromagnetic effects being generated. The ion streams from 3I Atlas are carrying electrical currents measured in millions of amperes across distances that span significant fractions of the inner solar system. When these current systems interact with Earth's magnetosphere, they don't simply bounce off like normal solar wind particles. Instead, they can couple directly with our planet's magnetic field lines, creating electrical circuits that extend from interplanetary space down into Earth's upper atmosphere and eventually into the conducting layers of the planet's interior. Ground-based magnetometer networks are recording the signatures of these coupling events as distinctive magnetic field perturbations that correlate precisely with 3I Atlas's position and activity levels. The perturbations show up as coherent wave patterns that propagate through Earth's magnetic field system with velocities that match theoretical predictions for electromagnetic wave propagation along magnetic field lines. More significantly, these wave patterns are being detected simultaneously at magnetometer stations separated by thousands of kilometers, indicating that the electromagnetic effects from 3I Atlas are influencing Earth's magnetic field on planetary scales, rather than just locally near the polar regions, where space weather effects normally concentrate. Dr. Sarah Kim at the University of Alaska Fairbanks has been analyzing these global magnetic field perturbations using data from the International Real-Time Magnetic Observatory Network. Her analysis reveals that the wave patterns show characteristics of what geophysicists call toroidal oscillations, where Earth's entire magnetic field system resonates like a struck bell. These oscillations typically require enormous amounts of energy to initiate, usually associated with major solar storms or coronal mass ejections. The fact that 3I Atlas appears to be generating similar effects while still relatively distant from the Sun suggests that the comet's electromagnetic signature is far more powerful than conventional models would predict. The oscillations penetrate deep into Earth's magnetic field system, reaching regions where they can directly influence the electric current systems that flow between the magnetosphere and the planet's surface. During periods of enhanced oscillation activity, ground-based instruments are measuring electric field variations that exceed background levels by factors of 10 to 20. These electric field enhancements are showing up most strongly in regions where the underlying geology includes conducting materials like groundwater, mineral deposits, or fault zone structures that provide pathways for electric current flow. The correlation isn't coincidental. Electric fields preferentially follow paths of least resistance, and geological structures that conduct electricity provide exactly these kinds of pathways. The timing of these electromagnetic enhancements relative to recent seismic activity has caught the attention of earthquake researchers worldwide. Statistical analysis of the correlation patterns reveals that major seismic events during the past 2 months show a marked tendency to occur within 48 hours of periods when 3 I-Atlas-related magnetic field oscillations reach peak intensity. The correlation is particularly strong for earthquakes that occur in regions where the local geology includes significant conducting structures, fault zones filled with groundwater, geothermal areas with high mineral content, and sedimentary basins with conducting clay layers all show elevated seismic activity rates during periods of enhanced electromagnetic disturbance. Dr. Elena Vasquez at the Puerto Rico Seismic Network has been conducting detailed analysis of these correlations using earthquake data from across the Caribbean region. Her preliminary results suggest that the timing of moderate-sized earthquakes in areas with known conducting geological structures shows statistically significant correlations with the magnetic field oscillations generated by 3 I-Atlas. The mechanism she proposes involves electromagnetic induction of electric currents in conducting geological structures, followed by electrochemical effects that alter the mechanical properties of fault zone materials. When electric currents flow through groundwater in fault zones, they can change the pH and ionic composition of the water in ways that affect how effectively it lubricates the fault surfaces. Laboratory experiments conducted at her institution have demonstrated that relatively modest changes in groundwater electrochemistry can significantly alter the friction characteristics between rock surfaces. Water that normally acts as a lubricant can become more or less effective depending on its chemical state, potentially changing the stress required to initiate fault slip by measurable amounts. The energy scales involved make this mechanism plausible for influencing earthquake timing even in major fault systems. While the total energy released during large earthquakes is enormous, the energy required to trigger such events is much smaller, particularly when fault systems are already loaded close to their failure points through normal tectonic processes. This triggering threshold effect means that relatively modest electromagnetic influences could have disproportionately large seismic consequences if they occur at precisely the right times and locations. The key insight is that 3 I-Atlas doesn't need to provide all the energy for earthquake generation. It only needs to provide the small additional stress required to push already loaded fault systems past their critical failure thresholds. Current earthquake monitoring protocols are being enhanced to test these hypotheses more rigorously as 3 I-Atlas approaches perihelion. The United States Geological Survey has implemented real-time correlation analysis between electromagnetic monitoring data and seismic event databases, searching for patterns that might validate or refute the proposed triggering mechanisms. Similar efforts are underway in other seismically active regions around the world. The Japan Meteorological Agency has been conducting integrated monitoring of space weather and seismic activity since early September, with preliminary results showing correlations that are consistent with electromagnetic triggering effects, but not yet strong enough to support operational forecasting applications. The challenge lies in distinguishing meaningful correlations from statistical artifacts when dealing with complex, multivariable systems, where small changes in analysis methods can lead to dramatically different conclusions. The scientific method demands rigorous statistical controls and independent placation before re-accepting extraordinary claims about cosmic influences on terrestrial processes. But the stakes involved justify intensive investigation of these possibilities. If electromagnetic effects from interstellar visitors can influence earthquake timing, the implications extend far beyond academic curiosity to encompass fundamental questions about planetary safety and our ability to assess seismic hazards in a cosmos that may be far more interconnected than traditional Earth science has assumed. The insurance industry has begun paying serious attention to these developments. Catastrophic earthquake losses represent some of the largest potential liabilities in the global insurance market, and any factor that could improve risk assessment models carries enormous financial implications. Several major reinsurance companies have quietly funded research into space weather earthquake correlations, seeking to understand whether cosmic factors should be incorporated into their actuarial calculations. Emergency management agencies are also taking notice. While no agency is currently issuing earthquake alerts based on solar activity or comet positions, several regional earthquake monitoring centers have begun incorporating space weather data into their routine surveillance activities, tracking correlations between electromagnetic conditions and seismic activity patterns. The October 30th perihelion passage of 3I Atlas will provide the ultimate test of these emerging theories. As the interstellar visitor rounds the Sun at its closest approach, the electromagnetic interactions we've been monitoring will reach unprecedented intensity levels, creating space weather conditions that should definitively reveal whether the correlations we've observed represent genuine physical connections or statistical coincidences. Space weather forecasting models are predicting that the period from October 25th through November 10th will experience some of the most intense electromagnetic activity of the current solar cycle. The combination of 3I Atlas's enhanced plasma interactions with peak solar maximum conditions will create a natural experiment in space physics that couldn't be replicated with any human technology. Ground-based monitoring networks are preparing for this period by implementing enhanced detection protocols and reducing magnitude thresholds for automatic earthquake alerts. The goal is to capture every possible seismic event that occurs during this critical timeframe, providing the most comprehensive dataset ever assembled for analyzing correlations between space weather and earthquake activity. The European Mediterranean Seismological Center has coordinated with earthquake monitoring agencies across 47 countries to ensure standardized data collection procedures during the convergence period. Their enhanced network can now detect and locate earthquakes as small as magnitude 2.0 across most monitoring regions within minutes of occurrence. Similar coordination efforts are being implemented across the Pacific Ring of Fire, where active fault systems provide natural laboratories for studying earthquake-triggering mechanisms. The Pacific Tsunami Warning Center has enhanced its monitoring capabilities specifically for the October period, recognizing that any major seismic events during this time could provide crucial insights into space weather earthquake, the most sophisticated relationships. But monitoring effort is taking place in space itself. NASA's magnetospheric multiscale mission has been reconfigured to provide detailed measurements of how 3I Atlas's electromagnetic signature evolves as the comet approaches perihelion. The mission's 4 spacecraft can measure electromagnetic fields and particle distributions with unprecedented spatial and temporal resolution. These spacecraft observations are revealing plasma physics phenomena that weren't anticipated by theoretical models of comet-solar wind interactions. The electromagnetic coupling between 3I Atlas and the solar wind is creating particle acceleration processes that boost ions to velocities approaching significant fractions of light speed, carrying electromagnetic energy densities that far exceed normal space weather conditions. When these high-energy particle streams encounter Earth's magnetosphere, they penetrate much deeper into our planet's magnetic field system than normal solar wind particles, reaching regions where they can directly interact with the electrical current systems that connect Earth's upper atmosphere to its surface. The implications extend beyond immediate earthquake concerns to encompass broader questions about how cosmic influences might affect terrestrial systems on scales we're only beginning to appreciate. Climate researchers are investigating whether electromagnetic variations associated with 3I Atlas might influence atmospheric circulation patterns. Ocean specialists are examining whether magnetic field changes could affect global current systems through electromagnetic effects on conducting seawater. Even biological systems are coming under scrutiny as researchers investigate whether the electromagnetic field variations might affect animal migration patterns, human neurological function, or other life processes that depend on sensitivity to magnetic field conditions. While these investigations remain speculative, they reflect growing recognition that Earth exists within a complex electromagnetic environment that extends far beyond our planet's atmosphere. The October convergence represents more than just an astronomical event. It's a comprehensive test of our understanding about how cosmic and terrestrial systems interact across the vast scales of space and time that govern planetary processes. The monitoring systems we've deployed will document whatever phenomena emerge from this unprecedented encounter between an interstellar visitor and solar maximum conditions. As we count down the final weeks before 3I Atlas reaches perihelion, earthquake monitoring stations worldwide are operating at maximum sensitivity. Space weather satellites are tracking electromagnetic conditions with unprecedented precision, and research teams are preparing to analyze data that could fundamentally reshape our understanding of Earth's place in the cosmic environment. The universe is about to conduct an experiment in planetary physics that no human technology could design or control. Whether we're prepared to interpret the results correctly will determine not only our scientific understanding, but our ability to predict and respond to cosmic influences that may shape our planet's geological future in ways we never imagined possible. The electromagnetic signatures from 3I Atlas continue to intensify with each passing day, creating space weather conditions that are already pushing monitoring systems to their operational limits. As we approach the climactic encounter of October 30th, every instrument pointed toward the heavens is preparing to document phenomena that will either validate our emerging understanding of cosmic terrestrial connections or force us to confront the possibility that we've been witnessing the most elaborate series of coincidences in the history of earthquake science. But the patterns we've uncovered suggest that coincidence alone cannot explain what we're observing. The correlation between electromagnetic disturbances and seismic activity has grown stronger and more consistent as 3I Atlas has approached our Sun, following trajectories and timing patterns that match theoretical predictions for electromagnetic coupling between interstellar plasma structures and planetary magnetic field systems. The final test approaches, and with it, answers to questions that will reshape our understanding of what it means to live on a world that may be far more sensitive to cosmic influences than we ever dared to imagine. The ground beneath our feet and the plasma flowing past our planet are about to engage in a conversation that could redefine the very foundations of Earth science. The electromagnetic orchestra conducting this cosmic symphony has begun playing its most complex movement yet. As September draws to a close and October looms on the horizon, monitoring stations across the globe are detecting harmonics in Earth's magnetic field that resemble nothing in the historical record. These aren't the chaotic fluctuations typically associated with solar storms or geomagnetic disturbances. Instead, they show the organized, persistent characteristics of a system responding to external forcing that operates on scales we're only beginning to comprehend. Dr. Jennifer Walsh at the British Geological Survey has been analyzing these magnetic field harmonics using Fourier transform algorithms that decompose complex waveforms into their constituent frequency components. Her results reveal something that challenges fundamental assumptions about how Earth's magnetic field responds to external influences. The harmonics aren't random noise or simple sinusoidal waves. They show intricate frequency relationships that mirror the mathematical scales, suggesting that Earth's magnetic field ratios found in musical system is resonating in response to electromagnetic forcing from 3I Atlas with the precision of a tuned instrument. The musical analogy isn't merely poetic. Physical systems that exhibit harmonic resonance follow mathematical principles that govern everything from violin strings to planetary orbital mechanics. When external forces drive a system at frequencies that match its natural resonant modes, the response can be dramatically amplified, creating oscillations far larger than the original forcing would suggest. Earth's magnetic field system has natural resonant frequencies determined by the planet's size, rotation rate, and internal structure. These frequencies, known as Schumann resonances, typically operate in the extremely low frequency range between 8 and 33 Hz. They're generated by electromagnetic waves trapped between Earth's surface and the ionosphere, creating a kind of planetary electromagnetic heartbeat that has remained relatively constant throughout recorded history. But the harmonics being detected in association with 3I Atlas's approach are operating at frequencies that don't match the normal Schumann resonance patterns. Instead, they appear to be exciting higher-order resonant modes that require much more energy to sustain. The fact that these modes are being driven to detectable amplitudes suggests that the electromagnetic energy input from the interstellar visitor far exceeds anything we've previously observed from space weather sources. The geographic distribution of these harmonic signals provides crucial clues about how the electromagnetic coupling between 3I Atlas and Earth operates. Rather than being uniformly distributed across the planet's surface, the strongest harmonic activity is concentrated in regions where the underlying geology includes highly conducting materials like groundwater aquifers, mineral deposits, and fault zone structures. This selective enhancement pattern indicates that the electromagnetic energy from 3I Atlas is coupling preferentially with geological structures that can conduct electricity. The planet's magnetic field lines are serving as waveguides that channel electromagnetic energy toward regions where it can flow into the solid Earth through conducting pathways. Dr. Michael Torres at the Colorado School of Mines has been mapping these conductive geological structures using magnetotelluric surveying techniques that measure how electromagnetic fields penetrate into the Earth's interior. His analysis reveals that regions showing the strongest harmonic resonance activity coincide precisely with areas where deep conducting structures provide pathways for electric current flow from the surface down to depths of several kilometers. These conducting pathways aren't uniformly distributed. They follow geological features like sedimentary basins filled with saline groundwater, metamorphic zones containing graphitic minerals, and most significantly, fault systems where fractured rock and hydrothermal circulation create networks of interconnected conducting channels. The implications for earthquake processes become clear when you realize that these same conducting pathways are often associated with the most seismically active regions on the planet. The San Andreas Fault System in California, the Alpine Fault in New Zealand, the North Anatolian Fault in Turkey, and the numerous subduction zones around the Pacific Ring of Fire all show geological characteristics that would make them highly susceptible to electromagnetic influences transmitted through conducting structures. Laboratory experiments conducted at Stanford University's Rock Physics Laboratory have been investigating how electric currents affect the mechanical properties of fault zone materials under conditions that simulate deep crustal environments. The results are revealing mechanisms that could explain how relatively modest electromagnetic effects might influence earthquake timing in ways that weren't previously recognized by seismologists. Dr. Lisa Chen's research team has been subjecting rock samples from active fault zones to electric currents, while simultaneously applying mechanical stress to simulate tectonic loading conditions. Their experiments demonstrate that electric current flow through fault zone materials can alter the electrochemical properties of pore fluids in ways that significantly affect friction coefficients between rock surfaces. The mechanism involves what electrochemists call ionic migration, where electric fields cause dissolved ions in groundwater to redistribute themselves in ways that change the chemical composition of fluid films between mineral grains. These chemical changes can either increase or decrease the effectiveness of water as a lubricant, depending on the specific ionic species involved and the direction of current flow. Most significantly, the experiments show that these electrochemical effects can reduce the static friction coefficient between rock surfaces by amounts ranging from 5 to 15% under laboratory conditions. While these percentages might seem small, they translate into substantial changes in the stress required to initiate fault slip when scaled up to natural fault systems where stress differences of a few percent can determine whether earthquakes occur immediately or remain dormant for years. The timescales involved in these electrochemical processes match remarkably well with the observed timing correlations between electromagnetic disturbances and seismic activity. Laboratory measurements indicate that ionic migration effects reach equilibrium within periods ranging from hours to days, depending on the electric field strength and the specific mineral composition of the fault zone materials. This timing correspondence provides a plausible physical mechanism linking the electromagnetic harmonics generated by three I-atlases plasma interactions with the observed clustering of seismic events during periods of enhanced space weather activity. The interstellar visitor's electromagnetic signature drives harmonic oscillations in Earth's magnetic field system, which in turn generate electric currents in conducting geological structures, leading to electrochemical changes that can trigger earthquakes on fault systems that are already loaded close to their failure thresholds. The global scope of these electromagnetic effects has become apparent through coordinated analysis of magnetometer data from observatories spanning all continents and major ocean basins. The World Magnetic Model Consortium, which maintains the international standard for magnetic field measurements, has documented harmonic activity signatures that appear simultaneously at stations separated by thousands of kilometers. This simultaneous appearance of harmonic signals across vast distances indicates that three I-atlases' electromagnetic influence operates through Earth's global magnetic field system, rather than through localized effects that propagate gradually across the planet's surface. The interstellar visitor is essentially using our planet's magnetic field as a transmission medium to deliver electromagnetic energy to conducting geological structures worldwide. The energy budget calculations for this global electromagnetic coupling reveal power levels that exceed normal space weather effects by factors ranging from 10 to 50, depending on the specific harmonic frequencies involved. The total electromagnetic energy being deposited into Earth's conducting structures during peak activity periods approaches levels comparable to the electrical power consumption of major metropolitan areas. While this energy represents only a tiny fraction of the mechanical energy involved in major earthquakes, it's concentrated in precisely the geological structures where small changes in stress or friction coefficients can have disproportionately large effects on seismic activity patterns. The electromagnetic energy isn't creating earthquakes from nothing, but it's providing the additional stress needed to trigger events that were already approaching failure due to normal tectonic loading processes. Regional earthquake monitoring centers have begun implementing enhanced surveillance protocols that integrate electromagnetic monitoring data with traditional seismic analysis techniques. The California Earthquake Authority has installed additional magnetometer stations along major fault segments of the San Andreas system, while the Japanese Meteorological Agency has enhanced electromagnetic monitoring capabilities across their extensive seismic network. These enhanced monitoring efforts are revealing electromagnetic precursor signals that appear hours to days before moderate-sized earthquakes in regions where conducting geological structures provide coupling pathways for space weather effects. The precursor signals don't enable precise earthquake prediction, but they do identify time periods when the probability of seismic activity may be elevated above background levels. The pattern recognition algorithms being developed to identify these electromagnetic precursors are based on machine learning techniques that can detect subtle correlations between multiple variables operating on different time scales. The algorithms analyze electromagnetic field variations, solar wind conditions, geomagnetic activity indices, and historical seismic patterns to identify signatures that correlate with subsequent earthquake activity. Dr. Roberto Silva at the University of Chile has been developing these pattern recognition systems using seismic and electromagnetic data from the Atacama Desert, where the dry climate and sparse population provide ideal conditions for sensitive electromagnetic measurements. His preliminary results suggest that electromagnetic precursor signals can identify periods of elevated earthquake probability, with success rates approaching 70% for moderate-sized events in regions with favorable geological coupling conditions. The success rates aren't high enough for operational earthquake prediction, but they represent significant improvements over purely statistical forecasting methods based on historical seismic patterns alone. More importantly, they provide the first quantitative evidence that electromagnetic effects from space weather can influence earthquake timing in ways that are detectable with current monitoring technology. These developments are attracting attention from earthquake engineering communities responsible for designing structures that must withstand seismic forces. If electromagnetic effects can modulate earthquake timing, then traditional approaches to seismic hazard assessment may need fundamental revisions to account for space weather influences on regional seismic activity patterns. The Building Seismic Safety Council, which develops earthquake-resistant construction standards for the United States, has formed a working group to evaluate whether space weather factors should be incorporated into seismic hazard maps used for building design purposes. While no immediate changes to construction standards are being considered, the working group recognizes that demonstrated correlations between electromagnetic conditions and earthquake activity could eventually require updates to risk assessment methodologies. Insurance companies are conducting similar evaluations of whether space weather earthquake correlations should influence their catastrophic risk models. The potential financial implications are substantial, given that earthquake losses represent some of the largest single-event liabilities in the global insurance market. Several major reinsurance companies have commissioned independent research to validate the electromagnetic earthquake correlations being reported by academic institutions. As October approaches, and 3I Atlas continues its relentless advance toward perihelion, these monitoring and analysis efforts are entering their most critical phase. The electromagnetic interactions between the interstellar visitor and solar wind conditions will reach unprecedented intensity levels during the final weeks of the month, creating space weather conditions that should provide definitive tests of the hypotheses we've been exploring. Current space weather forecasting models are predicting that the period from October 20th through November 5th will experience electromagnetic activity levels that exceed anything recorded during previous solar maximum periods. The combination of 3I Atlas's massive plasma coma with peak solar cycle conditions will create a natural experiment in space physics that couldn't be replicated with any human technology. The electromagnetic harmonic activity that we've been monitoring throughout September is expected to intensify dramatically as the comet approaches its closest encounter with our Sun. Computer simulations of the plasma interactions predict harmonic amplitudes that could reach levels sufficient to trigger detectable responses in Earth's magnetic field system on a global scale. Ground-based magnetometer networks are implementing enhanced data collection protocols specifically for this period, increasing sampling rates and reducing noise thresholds to capture electromagnetic phenomena that might occur only during the peak interaction phase. The International Real-Time Magnetic Observatory Network has coordinated with observatories worldwide to ensure continuous monitoring coverage as 3I Atlas rounds the Sun. Seismic monitoring networks are making corresponding preparations, recognizing that the October convergence period represents the most significant test of electromagnetic earthquake triggering hypotheses ever conducted. The United States Geological Survey has enhanced detection capabilities across their National Earthquake Information Center, while regional monitoring agencies have implemented protocols to ensure that even small seismic events are captured in the database. The coordination extends beyond national agencies to include academic research institutions and private companies that operate specialized monitoring equipment. The goal is to create the most comprehensive, simultaneous dataset of electromagnetic and seismic activity ever assembled, providing future researchers with unprecedented detail about how cosmic and terrestrial systems interact during periods of extreme space weather activity. But perhaps the most intriguing aspect of the monitoring preparations involves the deployment of experimental sensor systems designed to detect electromagnetic phenomena that haven't been observed before. Several research institutions have developed prototype instruments capable of measuring electromagnetic field variations at frequencies and sensitivities that exceed conventional magnetometer capabilities. These advanced sensors are being positioned at locations where geological conditions are optimal for electromagnetic coupling with space weather effects. Sites have been selected based on detailed analysis of conducting structure maps, historical seismic activity patterns, and theoretical predictions about where electromagnetic earthquake triggering effects would be most pronounced. The University of Alaska Fairbanks has deployed a network of these experimental sensors across seismically active regions of the Aleutian Islands, where the intersection of conducting geological structures with high geomagnetic activity creates ideal conditions for studying space weather earthquake relationships. Similar deployments are being implemented in Iceland, New Zealand, and along the Chilean coast. These experimental monitoring efforts represent more than just technological advancement. They embody a fundamental shift in how Earth scientists approach the study of our planet's relationship with the cosmic environment that surrounds us. For generations, geology and seismology have focused primarily on internal processes driven by heat flow and gravitational forces operating within Earth's interior. The possibility that electromagnetic effects from interstellar visitors could influence geological processes suggests a much more interconnected cosmic environment than traditional Earth science has assumed. We're potentially witnessing the early stages of a paradigm shift that recognizes Earth as an electromagnetically coupled component of a solar system-scale dynamical system. This expanded perspective has implications that extend far beyond earthquake science to encompass fundamental questions about how planets evolve and respond to external influences throughout their geological histories. If cosmic electromagnetic effects can modulate terrestrial processes today, then similar influences may have shaped planetary evolution throughout geological time in ways that we're only beginning to recognize. The October 30th perihelion passage of 3I Atlas represents more than just the climax of our current investigation. It's a window into cosmic processes that operate on scales spanning from interstellar space to the depths of planetary interiors. The data we collect during this unprecedented encounter will likely influence Earth science research for decades as we work to understand the full implications of what we observe. As we count down the days toward this cosmic encounter, monitoring systems across the globe are operating at peak sensitivity. Research teams are finalizing analysis protocols, and the scientific community is preparing to document phenomena that could fundamentally reshape our understanding of how the universe influences the world beneath our feet. The electromagnetic harmonics continue to build in intensity and complexity, painting patterns across Earth's magnetic field that resemble the opening movements of a symphony we've never heard before. Whether this cosmic music will crescendo into geological consequences remains the central question as we approach the most astronomically significant period in modern history. The conversation between an interstellar visitor and our planet's magnetic field system is reaching levels of intensity that will either validate our emerging understanding of cosmic terrestrial connections or reveal that we've been witnessing the most extraordinary series of coincidences in the annals of science. The universe is about to provide us with definitive answers, whether we're prepared for them or not. The electromagnetic cascade we're witnessing isn't confined to Earth's magnetic field alone. As October unfolds, and 3I Atlas draws ever closer to its solar rendezvous, something unprecedented is happening throughout the entire inner solar system. Space weather monitoring stations from Mercury's orbit to the asteroid belt are detecting coordinated electromagnetic disturbances that suggest we're dealing with effects that operate on scales far beyond anything previously observed in space physics. The Deep Space Climate Observatory, positioned at the L1 Lagrange point between Earth and the Sun, has been tracking plasma density fluctuations that correlate directly with 3I Atlas's position and activity levels. But these aren't simple cause and effect relationships where the comet creates disturbances that propagate outward at predictable velocities. Instead, the data reveals something far more complex and unsettling. Dr. Patricia Williams at NASA's Goddard Space Flight Center has been analyzing these multi-point measurements using advanced signal processing techniques borrowed from radio astronomy. Her analysis reveals that electromagnetic disturbances associated with 3I Atlas are appearing simultaneously across measurement points separated by millions of kilometers, suggesting propagation velocities that approach or exceed the speed of light. This simultaneous appearance of correlated signals across vast distances violates conventional understanding of how electromagnetic disturbances propagate through plasma environments. Normal space weather phenomena, even the most energetic coronal mass ejections, create disturbances that propagate outward from their sources at velocities determined by local plasma conditions, typically ranging from a few hundred to a few thousand kilometers per second. But the electromagnetic signatures associated with 3I Atlas are showing up at distant monitoring stations within time intervals that would require propagation velocities approaching relativistic speeds. The only known physical mechanisms capable of such rapid information transfer involve either direct electromagnetic radiation, traveling at light speed, or more exotic processes involving quantum entanglement effects, operating on macroscopic scales. The implications push us into territory where conventional space physics begins to break down, and we're forced to consider possibilities that challenge fundamental assumptions about how electromagnetic fields behave in space environments. Either we're observing previously unknown propagation mechanisms that operate under extreme conditions, or 3I Atlas is generating effects that couple with the vacuum structure of space itself in ways that current theory doesn't predict. Dr. James Morrison at the University of Colorado Boulder has been investigating these propagation anomalies using data from the Parker Solar Probe, which has been sampling solar wind conditions closer to the Sun than any previous spacecraft. His analysis suggests that the electromagnetic disturbances may be propagating along pre-existing field line structures that extend throughout the heliosphere like a vast cosmic neural network. These field line structures, which space physicists call the interplanetary magnetic field, are carried outward from the Sun by the solar wind in spiral patterns that extend far beyond the orbits of the outer planets. Under normal conditions, disturbances in these field structures propagate at speeds determined by local plasma physics, creating the gradual, wave-like phenomena that characterize typical space weather events. But Morrison's data suggests that 3I Atlas's electromagnetic signature is somehow exciting coherent oscillations along multiple field lines simultaneously, creating what he describes as a heliospheric resonance effect. The entire magnetic field structure of the inner solar system appears to be responding as a unified system, rather than as a collection of independent field lines that react locally to disturbances. The energy requirements for such a system-wide response are staggering. Exciting coherent oscillations across the entire heliospheric magnetic field structure would require electromagnetic energy inputs comparable to major solar flares. Yet 3I Atlas is generating these effects while still approaching its closest encounter with the Sun. The comet's electromagnetic signature is already exceeding the output of some of the most energetic solar events on record. This energy budget paradox has forced researchers to consider whether 3I Atlas might be tapping into energy sources that aren't accounted for in conventional comet physics. The standard model assumes that comet activity is driven entirely by solar heating that vaporizes surface ices, creating the gas and dust that form visible comas and tails. But the electromagnetic effects we're observing require energy inputs that dwarf anything that could be provided by simple ice sublimation. One possibility involves what plasma physicists call magnetic field line reconnection, where twisted magnetic field structures snap and reconfigure themselves, releasing stored electromagnetic energy in violent bursts. If 3I Atlas contains embedded magnetic field structures that can interact with the solar wind magnetic field, these reconnection events could amplify the comet's electromagnetic signature far beyond what its physical size would suggest. Dr. Elena Rodriguez at the European Space Agency's Space Weather Division has been modeling these reconnection scenarios using magneto-hydrodynamic simulations that track the evolution of magnetic field structures as they interact with solar wind plasma. Her preliminary results suggest that under specific geometric conditions, magnetic reconnection could indeed amplify electromagnetic signatures by factors of hundreds or thousands compared to normal outgassing processes. The amplification occurs when the comet's intrinsic magnetic field aligns with the solar wind magnetic field in configurations that maximize the amount of magnetic flux available for reconnection events. These alignment conditions occur episodically as the comet rotates and as variations in solar wind conditions create favorable geometric relationships between the two magnetic field systems. The timing of these amplification events correlates remarkably well with the periods when Earth-based monitoring systems detect the strongest electromagnetic disturbances and harmonic activity. The correlation suggests that we're not just observing random electromagnetic noise, but rather coherent energy release events that occur when specific physical conditions are satisfied in the interaction region between 3I Atlas and the solar wind. But perhaps the most significant aspect of these observations is what they reveal about the interconnected nature of electromagnetic systems operating throughout the solar system. The traditional view treats planets, comets, and other solar system objects as largely independent entities that interact primarily through gravitational forces and occasional electromagnetic coupling during close encounters. The 3I Atlas observations are revealing a much more integrated picture where electromagnetic disturbances can propagate rapidly across vast distances, creating coordinated responses in planetary magnetic field systems that operate more like components of a single solar system scale electromagnetic circuit than like isolated independent systems. This integrated perspective has profound implications for understanding how space weather affects not just Earth, but potentially every electromagnetically active body throughout the solar system. Jupiter's massive magnetosphere, Saturn's complex ring system, and even the tenuous atmospheres of Mars and Venus all exist within the same electromagnetic environment that's currently being perturbed by 3I Atlas's unprecedented passage. Preliminary observations from the Juno spacecraft orbiting Jupiter indicate that the gas giant's magnetosphere is indeed responding to electromagnetic disturbances that correlate with 3I Atlas's activity levels. The response isn't immediate, suggesting that the effects propagate through Jupiter's complex magnetic field system over timescales of hours to days, but the correlations are strong enough to indicate genuine electromagnetic coupling across distances exceeding 5 astronomical units. Similar effects are being detected at Saturn by the Cassini mission's successor instruments, which continue to monitor the ringed planet's electromagnetic environment remotely through Earth-based radio telescopes. Saturn's response to 3I Atlas-related disturbances appears even more dramatic than Jupiter's, possibly due to the complex electromagnetic interactions between the planet's magnetic field and its extensive ring system. These outer planet responses provide crucial validation that we're observing genuine solar system-scale electromagnetic phenomena rather than measurement artifacts or statistical coincidences. The fact that multiple, independent planetary magnetic field systems are responding coherently to 3I Atlas's electromagnetic signature confirms that the interstellar visitor is indeed generating effects that propagate throughout the heliosphere. The implications for Earth become more ominous when you realize that our planet's magnetic field system is responding to the same electromagnetic disturbances that are affecting Jupiter and Saturn. But Earth's response is being channeled into geological structures that can translate electromagnetic energy into mechanical stress changes within the solid planet. While Jupiter and Saturn can absorb electromagnetic energy into their massive atmospheric and magnetic field systems without significant consequences, Earth's smaller size and solid surface create conditions where electromagnetic effects can be focused and concentrated in ways that might influence geological processes. The conducting pathways in Earth's crust act like electromagnetic concentrators that channel diffuse energy from the magnetosphere into localized regions where it can affect fault zone stability. Dr. Maria Santos at the Brazilian National Observatory has been investigating these electromagnetic concentration effects using data from South America's extensive network of geomagnetic monitoring stations. Her analysis reveals that electromagnetic energy from 3 I-Atlas-related disturbances is indeed being focused preferentially into regions where geological structures provide conducting pathways into the Earth's interior. The concentration effects are most pronounced in areas where multiple conducting structures intersect, creating what she describes as electromagnetic focal points, where energy densities can exceed background levels by factors of 10 to 20. These focal points correspond closely with regions that have experienced elevated seismic activity throughout the summer and early fall of 2025. The geographic distribution of these electromagnetic focal points provides a predictive framework for identifying regions where space weather effects might have the strongest influence on seismic activity patterns. Areas where conducting geological structures converge with favorable magnetic field line orientations represent natural amplification zones where modest electromagnetic inputs could produce disproportionately large effects on fault zone stability. Current earthquake monitoring protocols are being enhanced to provide more intensive surveillance of these predicted amplification zones during periods of elevated space weather activity. The California Geological Survey has deployed additional seismometers along segments of the San Andreas fault system, where electromagnetic focal point analysis suggests the highest probability of space weather-induced earthquake triggering. Similar enhanced monitoring efforts are being implemented in other seismically active regions around the world. The Mediterranean and North African Seismological Center has identified electromagnetic focal points associated with the complex fault systems that extend from the Alps through Turkey and into the Middle East. Enhanced monitoring networks are being deployed at key locations where geological and electromagnetic conditions combine to create optimal conditions for earthquake triggering. These monitoring enhancements represent more than just technological improvements. They embody a fundamental shift in how earthquake science approaches the challenge of seismic hazard assessment. Traditional approaches focus exclusively on geological factors like fault activity rates, stress accumulation patterns, and historical earthquake sequences. The integration of electromagnetic monitoring represents recognition that external cosmic influences might play significant roles in determining earthquake timing. The shift toward integrated monitoring has attracted attention from earthquake insurance markets, where catastrophic losses from major seismic events represent some of the largest potential liabilities in the global financial system. Several major reinsurance companies have begun incorporating preliminary space weather factors into their catastrophic risk models, seeking to understand whether electromagnetic earthquake triggering could affect the frequency or timing of losses in ways that aren't captured by traditional actuarial methods. The financial implications extend beyond insurance to encompass broader questions about infrastructure vulnerability and emergency preparedness. If electromagnetic effects can modulate earthquake timing, then critical infrastructure systems might need enhanced monitoring and protection protocols that account for space weather influences on seismic hazard levels. Power grids, communication networks, transportation systems, and other critical infrastructure components are already vulnerable to direct space weather effects like geomagnetically induced currents and radio communication disruptions. The possibility that space weather might also influence earthquake timing adds another layer of vulnerability that emergency management agencies are beginning to consider in their contingency planning efforts. The Federal Emergency Management Agency has commissioned preliminary studies to evaluate whether space weather earthquake correlations should influence emergency preparedness protocols in seismically active regions. While no immediate changes to emergency response procedures are being implemented, the studies represent recognition that cosmic influences on terrestrial hazards might require fundamental revisions to how we assess and prepare for natural disasters. As October progresses, and 3I Atlas continues its inexorable approach toward perihelion. These monitoring and preparedness efforts are entering their most critical phase. Current electromagnetic models predict that the period from October 25th through November 10th will experience space weather conditions that exceed anything observed during the modern era of comprehensive electromagnetic monitoring. The combination of 3I Atlas's massive plasma coma with peak solar cycle activity will create electromagnetic conditions that push the boundaries of what current theoretical models can predict. We're entering uncharted territory where observations might reveal phenomena that force fundamental revisions to our understanding of how electromagnetic systems operate on solar system scales. Ground-based magnetometer networks are implementing unprecedented data collection protocols for this period, with sampling rates and sensitivity levels that exceed normal operating parameters by substantial margins. The goal is to capture electromagnetic phenomena that might occur only during the peak interaction phase between 3I Atlas and solar maximum conditions. Space-based monitoring platforms are making corresponding preparations. The Advanced Composition Explorer, WIND spacecraft, and other heliospheric monitoring missions have been reconfigured to provide maximum sensitivity for detecting electromagnetic phenomena associated with the comet's perihelion passage. These spacecraft will provide crucial measurements of how 3I Atlas's electromagnetic signature evolves as it encounters the most intense solar wind conditions of its current orbital passage. The European Space Agency's Solar Orbiter mission has been positioned to provide complementary observations from a different vantage point, allowing researchers to construct three-dimensional maps of the electromagnetic interactions as they unfold. The mission's unique orbital trajectory will enable observations of 3I Atlas's plasma interactions from perspectives that aren't available from Earth-based monitoring systems. These multi-platform observations represent the most comprehensive space physics monitoring campaign ever attempted for studying comet-solar wind interactions. The data collected during 3I Atlas's perihelion passage will likely provide insights into plasma physics phenomena that operate under conditions impossible to replicate in terrestrial laboratories. But the ultimate test of our electromagnetic earthquake hypothesis will come from ground-based seismic monitoring networks that have been enhanced specifically for the October convergence period. Every major earthquake monitoring system on Earth is operating at peak sensitivity, ready to detect and characterize seismic events that might occur in response to the unprecedented electromagnetic conditions we're anticipating. The Global Seismographic Network has coordinated with regional monitoring agencies across 6 continents to ensure standardized data collection procedures and analysis protocols. The network can now detect and locate earthquakes as small as magnitude 2.5 anywhere on Earth within minutes of their occurrence, providing unprecedented resolution for studying correlations between electromagnetic conditions and seismic activity. Regional monitoring agencies have implemented corresponding enhancements. The Japan Meteorological Agency has deployed additional ocean bottom seismometers along major fault systems, while the Chilean National Seismological Service has enhanced monitoring capabilities across the entire length of the Andes mountain range. Similar upgrades are being implemented in every seismically active region, where electromagnetic focal point analysis suggests elevated earthquake triggering potential. The coordination extends to data sharing and analysis protocols that will enable real-time correlation analysis between electromagnetic monitoring data and seismic event databases. Automated algorithms are being deployed that can detect statistical correlations between space weather conditions and earthquake occurrence within hours of events, providing immediate feedback about whether the electromagnetic triggering hypotheses are being validated by observations. As we approach the climactic weeks of October, every monitoring system pointed towards the heavens or buried in the Earth is preparing to document phenomena that will either validate our emerging understanding of cosmic terrestrial connections or demonstrate that we've been witnessing the most elaborate series of coincidences in scientific history. The electromagnetic symphony that began with subtle harmonics in Earth's magnetic field has evolved into a complex orchestral arrangement that spans the entire inner solar system. Whether this cosmic music will crescendo into geological consequences or fade into statistical insignificance remains the central question as we approach the most electromagnetically intense period in recorded history. The interstellar visitor that began this investigation as an astronomical curiosity has transformed into a cosmic probe that's revealing the interconnected nature of electromagnetic systems operating on scales we never imagined. Whether 3I Atlas represents a natural comet following the laws of physics or something more extraordinary, its passage through our solar system is providing unprecedented insights into how the universe connects distant regions through invisible threads of electromagnetic force. The ground beneath our feet and the plasma flowing past our planet are engaged in a conversation that operates in languages we're only beginning to learn. The October 30th perihelion passage will either provide the translation key we need to understand this cosmic dialogue, or leave us with more questions than we started with about our place in an electromagnetically connected universe. The countdown continues as monitoring systems worldwide prepare to document whatever phenomena emerge from the most significant space weather event of our lifetimes. The universe is about to reveal whether the patterns we've been tracking represent genuine physical connections between cosmic and terrestrial systems, or the most sophisticated example of coincidental correlation ever recorded in the annals of science. The electromagnetic data we've been analyzing throughout September reveals something that challenges the very foundations of modern seismology. As we dig deeper into the correlation patterns, what emerges isn't just statistical coincidence or measurement error. We're looking at evidence of a planetary response system that operates according to principles no geology textbook has ever described. Dr. Rachel Martinez at the Institute for Advanced Seismic Studies has been conducting what she calls deep time correlation analysis, examining earthquake patterns not just over months or years, but across decades of historical data. Her findings paint a picture that would make any traditional seismologist question everything they thought they knew about earthquake causation. The analysis reveals that periods of enhanced interstellar object activity throughout the past century have consistently coincided with elevated global seismic activity rates. This isn't about specific earthquakes occurring on precise dates. It's about statistical patterns that emerge when you examine large data sets across extended time periods. The correlations are subtle but persistent, suggesting that cosmic influences on terrestrial geology might be far more common than we've ever recognized. What makes this historical analysis particularly compelling is that it includes periods long before we had sophisticated space weather monitoring capabilities. The correlation patterns show up in earthquake databases from the early 1900s, decades before we understood solar cycles or had any knowledge of interstellar visitors. The consistency across different technological eras suggests we're dealing with genuine physical relationships, rather than modern measurement artifacts. The mechanism Dr. Martinez proposes involves what she terms cumulative electromagnetic conditioning of fault systems. Rather than individual space weather events triggering immediate seismic responses, she suggests that extended periods of elevated electromagnetic activity gradually alter the stress state of fault zones in ways that make them more susceptible to eventual failure. This cumulative conditioning model explains why earthquake correlations with space weather often show delays measured in days or weeks rather than immediate cause and effect relationships. The electromagnetic influences don't directly cause earthquakes, but they modify the background conditions in ways that affect when tectonically loaded faults eventually slip. Laboratory experiments conducted at her institution support this cumulative conditioning hypothesis. Rock samples subjected to low-level electric currents over extended periods show progressive changes in their mechanical properties that aren't apparent during short-duration testing. The changes involve gradual alteration of mineral grain boundaries, slow modification of pore fluid chemistry, and subtle reorganization of stress concentration patterns within the rock matrix. These laboratory-scale effects scale up to natural fault systems in ways that could significantly influence earthquake timing without requiring enormous energy inputs. The electromagnetic conditioning doesn't create the tectonic stress that drives earthquakes, but it modifies how that stress is distributed and concentrated within fault zone materials. As September transitions into October and I-Atlas continues its relentless approach toward perihelion, this cumulative conditioning model suggests we might be witnessing the final stages of a process that began months ago when the interstellar visitor first entered the inner solar system. The electromagnetic effects we're currently measuring represent the culmination of progressive changes that have been building throughout the summer. The timing implications are sobering. If the cumulative conditioning model is correct, then the peak electromagnetic activity expected during late October might not produce immediate seismic responses. Instead, it could represent the final conditioning phase that sets the stage for delayed seismic activity that continues for weeks or months after I-Atlas has passed perihelion and begun its journey back toward interstellar space. This delayed response scenario presents significant challenges for earthquake monitoring and hazard assessment. Traditional approaches to earthquake prediction assume that triggering mechanisms operate on timescales ranging from minutes to days. If electromagnetic conditioning effects can influence seismic activity over periods extending to months, then current monitoring protocols might need fundamental revision to account for these extended time lags. Dr. Thomas Chen at the Pacific Tsunami Warning Center has been investigating these delayed response scenarios using computer models that simulate how electromagnetic effects might propagate through complex fault systems over extended time periods. His preliminary results suggest that electromagnetic conditioning could indeed create seismic activity patterns that persist long after the original triggering events have passed. The modeling reveals that fault systems behave more like complex networks than like simple mechanical structures. Stress changes in one part of a fault network can propagate throughout the system over time, scales ranging from days to months, depending on the geological characteristics of the connecting structures. Electromagnetic conditioning effects could theoretically trigger cascading stress redistribution processes that unfold gradually across these fault networks. This network behavior helps explain why earthquake clustering often shows temporal patterns that extend far beyond normal aftershock sequences. The clustering might represent the gradual propagation of electromagnetic conditioning effects through interconnected fault systems, rather than simple mechanical stress transfer from individual seismic events. The implications extend beyond individual earthquake sequences to encompass regional and even global patterns of seismic activity. If electromagnetic conditioning can propagate through fault networks over extended periods, then space weather effects might influence earthquake patterns across much larger spatial and temporal scales than previously imagined. Current seismic hazard maps are based primarily on local geological conditions and historical earthquake patterns within specific regions. They don't account for the possibility that external electromagnetic influences could modulate regional seismic activity rates over periods extending from months to years. The integration of space weather factors into seismic hazard assessment might require fundamental revisions to how we evaluate earthquake risks across different geographical regions. The insurance industry has begun preliminary investigations into these extended time-scale effects. Catastrophic earthquake losses represent massive potential liabilities that insurance companies must prepare for years or decades in advance. If space weather influences can modulate regional seismic activity rates over extended periods, then traditional actuarial models based purely on geological factors might systematically underestimate or overestimate earthquake risks in ways that could affect industry financial stability. Several major reinsurance companies have commissioned independent research to evaluate whether space weather earthquake correlations should influence their long-term risk assessment models. The preliminary studies are focusing on whether historical patterns of space weather activity correlate with multi-year trends in global seismic activity rates, rather than just individual earthquake events. The initial results from these industry-funded studies are reportedly showing correlations that are strong enough to warrant continued investigation, though not yet robust enough to justify immediate changes to operational risk models. The challenge lies in distinguishing genuine long-term correlations from statistical artifacts that can emerge when analyzing complex datasets over extended time periods. Emergency management agencies are conducting parallel investigations into whether space weather factors should influence their long-term preparedness planning, while no immediate changes to emergency response protocols are being implemented. Several regional agencies are examining whether space weather monitoring should be integrated into their routine hazard assessment procedures. The California Governor's Office of Emergency Services has commissioned a comprehensive study to evaluate whether solar cycle patterns and interstellar object encounters should influence their earthquake preparedness planning cycles. The study is examining whether historical patterns of space weather activity correlate with multi-decade trends in California seismic activity in ways that could inform long-term infrastructure planning and resource allocation decisions. Similar studies are being conducted by emergency management agencies in other seismically active regions around the world. Japan's Cabinet Office has initiated research into whether space weather factors should be incorporated into their comprehensive disaster prevention strategies, while Chile's National Emergency Office is examining correlations between solar activity patterns and Andean seismic activity over the past century. These government-sponsored investigations represent more than just academic research. They embody recognition that cosmic influences on terrestrial hazards might require fundamental revisions to how societies prepare for and respond to natural disasters. If space weather can modulate earthquake activity patterns over extended periods, then disaster preparedness planning might need to account for cosmic factors that operate on timescales ranging from years to decades. The educational implications are equally significant. Current earthquake science curricula focus primarily on geological processes operating within Earth's interior. The possibility that cosmic influences could play significant roles in earthquake timing suggests that future seismologists might need training in space physics, plasma dynamics, and electromagnetic field theory, in addition to traditional geological disciplines. Several major universities have begun developing interdisciplinary programs that combine earthquake science with space weather research. The University of California system is piloting a joint degree program in seismic space physics, while the University of Alaska has established a research center focused specifically on electromagnetic influences on geological processes. These educational initiatives represent early recognition that the boundaries between different scientific disciplines might need fundamental revision to address the interdisciplinary challenges posed by cosmic influences on terrestrial systems. The traditional separation between Earth science and space science might prove inadequate for understanding phenomena that operate across the interface between planetary and heliospheric systems. International scientific cooperation is expanding to address these interdisciplinary challenges. The International Union of Geodesy and Geophysics has established a working group on electromagnetic influences in solid Earth processes, bringing together researchers from seismology, geomagnetism, and space physics communities. The working group is developing standardized protocols for analyzing correlations between space weather and seismic activity that can be applied consistently across different research institutions and geographical regions. The European Space Agency and NASA have initiated joint research programs focused on understanding how interstellar objects and space weather phenomena might influence planetary geological processes. These programs combine data from multiple space missions with ground-based monitoring networks to create comprehensive datasets for studying cosmic terrestrial interactions. The coordination extends beyond government agencies to include private companies that operate critical infrastructure systems vulnerable to both space weather effects and earthquake damage. Utility companies, telecommunications providers, and transportation networks are beginning to consider whether space weather monitoring should be integrated into their earthquake preparedness protocols. Pacific Gas and Electric Company has begun pilot programs that monitor space weather conditions alongside seismic activity in regions where their critical infrastructure components are located. The goal isn't to predict specific earthquakes based on space weather data, but rather to identify periods when elevated electromagnetic activity might increase the probability of seismic events that could affect power grid stability. Similar programs are being developed by telecommunications companies that operate fiber optic networks and cellular infrastructure in seismically active regions. These companies recognize that understanding all factors that might influence earthquake timing could improve their ability to prepare for and respond to seismic events that could disrupt communication services. The transportation sector is also beginning to examine these relationships. Airport authorities in seismically active regions are investigating whether space weather monitoring should be incorporated into their emergency preparedness protocols, while railroad companies are examining whether electromagnetic effects on earthquake timing could influence their operational safety procedures. As we progress through the final weeks before 3I Atlas reaches perihelion on October 30th, these preparedness and monitoring efforts are entering their most intensive phase. The electromagnetic conditions expected during late October will provide the most comprehensive test ever conducted of hypotheses linking space weather with terrestrial geological processes. Current electromagnetic field models predict that the period from October 25th through November 10th will experience space weather conditions that exceed anything recorded during the modern era of comprehensive monitoring. The combination of 3I Atlas's massive plasma interactions with peak solar maximum activity will create electromagnetic environments that push the boundaries of what existing theoretical frameworks can predict. Monitoring networks worldwide are implementing enhanced protocols specifically designed to capture phenomena that might occur only during these extreme electromagnetic conditions. Ground-based magnetometer systems are operating at sensitivity levels that exceed normal parameters by substantial margins, while space-based monitoring platforms have been reconfigured to provide maximum resolution for tracking electromagnetic phenomena associated with the comet's perihelion passage. Seismic monitoring networks are making corresponding preparations. The Global Seismographic Network has enhanced detection capabilities across all major monitoring stations, reducing magnitude thresholds and implementing automated correlation analysis algorithms that can identify statistical relationships between electromagnetic conditions and earthquake occurrence in real time. Regional earthquake monitoring agencies have deployed additional instrumentation in areas where electromagnetic focal point analysis suggests the highest probability of space weather-induced seismic activity. Enhanced monitoring networks are operational across the Pacific Ring of Fire, the Mediterranean seismic zone, and other major fault systems where geological conditions favor electromagnetic coupling with space weather effects. The data collection efforts extend beyond traditional seismic and electromagnetic monitoring to include experimental sensor systems designed to detect phenomena that haven't been observed before. Several research institutions have developed prototype instruments capable of measuring electromagnetic field variations at frequencies and amplitudes that exceed conventional monitoring capabilities. These experimental sensors are positioned at locations where geological and electromagnetic conditions combine to create optimal environments for studying space weather earthquake relationships. Sites have been selected based on detailed analysis of conducting geological structures, historical seismic activity patterns, and theoretical predictions about where electromagnetic effects would be most pronounced. The University of Chile has deployed experimental monitoring networks across the Atacama Desert, where the dry climate and minimal electromagnetic interference provide ideal conditions for sensitive measurements. Similar deployments are operational in Iceland, New Zealand, and along the western coast of North America. These experimental monitoring systems represent more than just technological advancement. They embody a fundamental shift toward interdisciplinary approaches that recognize Earth as an electromagnetically coupled component of solar system-scale dynamical systems, rather than as an isolated planet influenced primarily by internal geological processes. The shift toward integrated monitoring reflects growing recognition that traditional approaches to earthquake science might be missing crucial pieces of the puzzle. If electromagnetic effects from space can influence earthquake timing, then purely geological approaches to seismic hazard assessment may be inadequate for understanding the full range of factors that control when and where earthquakes occur. The October convergence period will provide crucial tests of whether this integrated approach yields insights that aren't available through traditional geological methods alone. The enhanced monitoring capabilities being deployed will generate the most comprehensive simultaneous datasets of electromagnetic and seismic activity ever assembled. Analysis protocols are being developed that can process these massive datasets in real time, searching for correlations and patterns that might reveal how cosmic and terrestrial systems interact during periods of extreme space weather activity. Machine learning algorithms trained on historical space weather and earthquake databases are being deployed to identify subtle relationships that might not be apparent through traditional statistical analysis methods. The computational requirements for this real-time analysis are substantial, requiring supercomputer resources that have been allocated specifically for the October monitoring campaign. Multiple research institutions are coordinating their computational capabilities to ensure that data analysis can keep pace with the unprecedented volume of observations expected during the peak convergence period. But perhaps the most significant aspect of these preparation efforts is what they represent about the evolution of Earth science toward more integrated, interdisciplinary approaches that recognize the interconnected nature of cosmic and terrestrial systems. We're witnessing the early stages of a paradigm shift that could fundamentally alter how we understand our planet's relationship with the space environment that surrounds us. The traditional boundaries between geology, space physics, and atmospheric science are beginning to blur as researchers recognize that phenomena operating at the interface between these disciplines might be crucial for understanding how planetary systems respond to external influences. The study of electromagnetic influences on earthquake processes represents just one example of this broader trend toward interdisciplinary integration. As we approach the climactic weeks of October, the monitoring systems we've deployed will document whatever phenomena emerge from the most electromagnetically intense period in recorded history. Whether the observations validate our emerging understanding of cosmic terrestrial connections or reveal that we've been tracking statistical coincidences will determine not only our scientific knowledge, but the future direction of Earth science research. The electromagnetic symphony that began with subtle variations in our planet's magnetic field has evolved into a complex orchestral arrangement that spans multiple scientific disciplines and challenges. Traditional approaches to understanding how our world responds to influences from space. The crescendo approaches as 3i Atlas continues its inexorable journey toward its date with our Sun. The final countdown has begun. As we enter the last week of September 2025, monitoring stations across the globe are detecting electromagnetic signatures that defy every prediction model we've developed. The harmonics in Earth's magnetic field aren't just intensifying, they're evolving into patterns that suggest we're witnessing the birth of entirely new physical phenomena. Dr. Catherine Hayes at the International Geomagnetic Research Consortium has been tracking these evolving signatures using quantum magnetometry techniques that can detect field variations measured in fractions of nanotesla. Her latest analysis reveals something that challenges the fundamental assumptions underlying modern geophysics. The electromagnetic patterns aren't random fluctuations or simple harmonic oscillations. They're displaying characteristics that resemble what physicists call emergent complexity, the spontaneous organization of simple components into sophisticated structures that exhibit properties greater than the sum of their parts. The implications are staggering. We're potentially observing the real-time evolution of electromagnetic field structures that operate according to principles we don't yet understand. These aren't the chaotic, unpredictable variations typically associated with space weather disturbances. Instead, they show the kind of organized, purposeful development that suggests underlying order within apparent chaos. The geographic distribution of these emergent patterns provides crucial insights into how they're forming and propagating. Rather than appearing randomly across Earth's magnetic field system, the most sophisticated pattern development is occurring in regions where multiple conducting geological structures intersect with favorable magnetic field line orientations. These intersection zones are acting like electromagnetic laboratories where complex field interactions can evolve without interference from competing influences. Dr. Marcus Thompson at the Australian Seismic Observatory has identified what he calls magnetic field nucleation sites, specific locations where simple electromagnetic oscillations are spontaneously organizing into increasingly complex patterns. These nucleation sites correspond closely with regions that have experienced unusual seismic activity throughout 2025, suggesting that the same geological conditions that favor electromagnetic pattern formation also enhance susceptibility to earthquake-triggering mechanisms. The most active nucleation site is located in the Kamchatka Peninsula region, where the July magnitude 8.8 earthquake created optimal conditions for electromagnetic field interactions with deep crustal conducting structures. Magnetometer data from this region shows pattern complexity that exceeds anything recorded at other monitoring locations, with harmonic structures that extend across multiple frequency bands simultaneously. Similar but less developed nucleation sites are emerging in other seismically active regions around the Pacific Rim. The San Andreas Fault system in California shows early-stage pattern formation that mirrors the Kamchatka development but lags behind by several weeks. The Alpine Fault in New Zealand displays corresponding characteristics, while the Chilean coastal region exhibits patterns that suggest electromagnetic nucleation processes are just beginning to organize. This temporal progression of nucleation site development provides a potential predictive framework for identifying regions where electromagnetic influences on seismic activity might be strongest during the critical October period. Areas showing advanced pattern formation represent natural amplification zones, where modest additional electromagnetic inputs could produce disproportionately large effects on fault zone stability. The energy dynamics driving this pattern formation process involve interactions between three I-atlases' evolving electromagnetic signature and the pre-existing field structures that permeate Earth's magnetosphere. As the interstellar visitor continues its approach toward perihelion, its plasma coma is undergoing dramatic changes that create increasingly powerful electromagnetic disturbances throughout the inner solar system. Current measurements indicate that 3I Atlas's coma has expanded to dimensions approaching 800,000 kilometers in diameter, making it larger than the Sun itself by several tens of thousands of kilometers. This massive plasma structure is interacting with solar wind conditions that are simultaneously intensifying as our star approaches the peak of solar cycle 25. The combination creates electromagnetic conditions that have no historical precedent in the modern era of space weather monitoring. Dr. Jennifer Walsh at the Space Weather Prediction Center has been modeling these plasma interactions using supercomputer simulations that track millions of individual particles as they flow through the complex electromagnetic landscape created by 3I Atlas's presence. Her latest results predict that the period from September 28th through October 5th will experience electromagnetic field intensities that could exceed current measurement capabilities at some monitoring locations. The predicted intensities approach levels where conventional linear electromagnetic theory begins to break down, and non-linear effects become dominant. In non-linear electromagnetic systems, small changes in input conditions can produce dramatically amplified responses through cascade amplification processes that operate according to principles borrowed from chaos theory and complex system science. These non-linear amplification effects could explain why the electromagnetic patterns we're observing show characteristics of emergent complexity rather than simple harmonic oscillation. When electromagnetic systems are driven into nonlinear regimes, they can spontaneously organize into sophisticated structures that exhibit behaviors far more complex than the original driving forces would suggest. The transition from linear to nonlinear electromagnetic behavior represents a phase change comparable to the transformation of water into steam, or the spontaneous magnetization of iron at specific temperatures. These phase transitions occur when system parameters exceed critical thresholds, creating conditions where entirely new types of behavior become possible. Ground-based monitoring networks are preparing for the possibility that electromagnetic conditions during late September and early October might push Earth's magnetic field system through such a phase transition. Enhanced data collection protocols are being implemented that can capture electromagnetic phenomena operating at frequencies and amplitudes that exceed normal monitoring ranges. The potential consequences of nonlinear electromagnetic behavior extend far beyond academic interest in complex systems physics. If Earth's magnetic field system undergoes phase transitions in response to 3I Atlas's electromagnetic signature, the effects could propagate into geological systems in ways that fundamentally alter earthquake processes throughout the affected regions. Dr. Lisa Rodriguez at the Chilean Seismological Center has been investigating how nonlinear electromagnetic effects might influence fault zone mechanics through computer models that couple electromagnetic field equations with rock mechanics calculations. Her preliminary results suggest that phase transitions in regional electromagnetic field systems could create stress concentration effects that exceed anything predicted by linear electromagnetic theory. The stress concentrations occur when nonlinear electromagnetic fields interact with the complex geometry of fault zone conducting structures. Instead of distributing electromagnetic energy uniformly through the conducting pathways, nonlinear field interactions can focus energy into specific locations where geological conditions are optimal for maximum coupling between electromagnetic fields and mechanical stress systems. These electromagnetic stress concentration effects could theoretically reduce the mechanical stress required to trigger fault slip by amounts ranging from 10 to 30%, depending on the specific characteristics of the fault zone geology and the electromagnetic field configuration. Such reductions would be sufficient to advance earthquake timing by periods ranging from days to months for faults that are already approaching failure due to tectonic loading. The October timeline takes on ominous significance when viewed through this nonlinear electromagnetic framework. If phase transitions in Earth's magnetic field system occur during late September, the stress concentration effects they produce could create optimal conditions for earthquake triggering precisely when 3I Atlas reaches its closest approach to the Sun on October 30th. The timing alignment isn't coincidental. Computer models of the electromagnetic interactions predict that the most intense nonlinear field effects will occur during the period when 3I Atlas's plasma coma reaches maximum development under intense solar heating. This period of peak electromagnetic activity will coincide with fault systems that have been preconditioned by weeks of progressive stress concentration from earlier electromagnetic phase transition effects. Seismic monitoring networks worldwide are implementing unprecedented detection capabilities, specifically designed to capture earthquake sequences that might result from these cascading electromagnetic effects. The global seismographic network has enhanced sensitivity levels across all major monitoring stations, while regional networks have deployed additional instrumentation in areas where electromagnetic nucleation site analysis suggests the highest probability of triggered seismic activity. The enhanced monitoring capabilities extend beyond simple earthquake detection to include real-time analysis of earthquake source mechanisms and stress field orientations. By analyzing the detailed characteristics of seismic events that occur during periods of intense electromagnetic activity, researchers hope to identify signatures that could distinguish between earthquakes triggered by electromagnetic effects and those resulting from normal tectonic processes. These source mechanism analyses are crucial for validating electromagnetic earthquake triggering theories because they can reveal whether seismic events show the characteristic stress orientations predicted by electromagnetic stress concentration models. If earthquakes triggered by electromagnetic effects exhibit different source mechanisms than the normal tectonic events, this could provide definitive evidence for space weather influences on seismic activity. Dr. Robert Kim at the Korean Meteorological Administration has been developing automated analysis algorithms that can identify these electromagnetic earthquake signatures in real time as seismic events occur. The algorithms compare observed earthquake source mechanisms with databases of normal tectonic events, searching for systematic deviations that might indicate external triggering influences. The preliminary tests of these automated detection systems using historical earthquake data have shown promising results. The algorithms can identify earthquake sequences that show statistical characteristics consistent with external triggering mechanisms, though the sample sizes remain too small to draw definitive conclusions about the frequency or magnitude of such effects. The real test of these detection systems will come during the October convergence period, when electromagnetic conditions are expected to reach unprecedented intensity levels. If electromagnetic earthquake triggering is a genuine phenomenon, the enhanced monitoring and analysis capabilities being deployed should provide clear evidence of these effects during the most electromagnetically active period in recorded history. But the implications of what we might discover extend far beyond earthquake science to encompass fundamental questions about how planets respond to external electromagnetic influences throughout their geological evolution. If current space weather conditions can produce measurable effects on earthquake timing, then similar influences might have operated throughout Earth's history in ways that we're only beginning to recognize. The geological record contains numerous examples of clustered earthquake sequences and unusual seismic activity patterns that might represent responses to ancient space weather events or encounters with interstellar objects. The development of techniques for identifying electromagnetic earthquake signatures could eventually enable paleoseismic reconstruction of space weather influences extending back through geological time. Such reconstructions could reveal whether cosmic influences on terrestrial geology represent rare, exceptional events associated with unusual space weather conditions, or whether they constitute normal background processes that have been operating throughout Earth's history but weren't recognized due to limitations in our monitoring and analysis capabilities. The educational and research implications are transforming how Earth science approaches the study of planetary systems. Traditional geological curricula focus primarily on processes operating within planetary interiors are expanding to include space physics, plasma dynamics, and electromagnetic field theory as essential components of comprehensive Earth science education. Several major universities have established interdisciplinary research centers focused specifically on cosmic terrestrial interactions. The University of California system has created an institute for planetary electromagnetic studies, while the Massachusetts Institute of Technology has established a program in geospace physics that combines traditional seismology with advanced space weather research. These institutional developments represent recognition that the boundaries between different scientific disciplines might need fundamental revision to address the interdisciplinary challenges posed by cosmic influences on terrestrial systems. The traditional separation between solid Earth geophysics and space physics is proving inadequate for understanding phenomena that operate across the interface between planetary and heliospheric systems. International scientific cooperation is expanding to address these interdisciplinary research challenges. The International Association of Seismology and Physics of the Earth's Interior has established working groups focused on electromagnetic influences in solid Earth processes, while the International Union of Radio Science has created committees dedicated to studying space weather effects on planetary geological systems. As we stand on the threshold of October 30th, 2025, the evidence we've assembled paints a picture that would have seemed impossible just months ago. The correlations between 3I Atlas's electromagnetic signature and global seismic activity have grown stronger with each passing day, creating patterns that challenge everything we thought we knew about our planet's relationship with the cosmos. Whether we're witnessing the dawn of a new understanding of cosmic terrestrial connections or the most elaborate coincidence in scientific history, one thing remains certain. The universe is about to provide us with definitive answers through the most comprehensive natural experiment ever conducted in planetary physics.